A single photon can cross the entire observable universe, and yet for the photon, the journey takes no time at all. It's the most familiar thing you've ever seen, and it behaves like nothing else in nature. So what is light really? An object, a wave, or something that slips through the cracks of time itself? Every time you open your eyes, the universe touches you, silently, precisely, and with rules that resist common sense. In that touch lives a paradox we can measure, predict, and use, yet still struggle to describe. Light seems gentle, almost forgiving, until you ask it to explain itself. It paints the edge of a shadow with perfect geometry, then blurs that edge into fringes no classical picture can keep. It travels as a spread of possibilities, then arrives as one unarguable event, a single, recorded click. And with each experiment, the same question returns, without raising its voice. What exactly is a photon? In this film, we will follow light as it moves from the familiar to the unforgivingly precise. We will begin where everyone begins, with sunlight on a wall and a quiet room growing bright. Then we will step backward through the long history of human sight, rays from the eye, waves in ether, and the first measurements that made light finite. From there, the story tightens. A heated cavity will demand an accounting that continuous waves cannot pay. Metal will release electrons in a way that ignores brightness, but obeys colour with ruthless consistency. And a simple apparatus, 2 narrow openings and a distant screen, will turn calm intuition into a careful, sleepless kind of wonder. We will treat the strangeness with patience, not spectacle, because the photon is not merely a tiny bead of energy, and it is not merely a ripple in space. It is what happens when quantum probability meets the electromagnetic field, and when both must still respect the geometry of spacetime. Along the way, we will watch interference appear from single events, see momentum carried without mass, and learn why a photon cannot be placed at rest, even in principle. As the picture sharpens, it also widens. Spectral lines will become barcodes for atoms and distant stars. Redshifts will become a clock for cosmic history. And faint, ancient light will reveal structures that no telescope can touch directly. Curvature, unseen matter, and the slow stretching of space itself. Yet even at the end, the photon will not become ordinary. The more carefully we define it, the more it reveals about measurement, about fields, and about the boundary between what is possible and what is actual. Tonight, we will let light be our guide, not to an easy answer, but to a deeper kind of clarity. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will move from everyday optics to quantum experiments, then outward into relativity and the modern field-based portrait of light. And as we follow photons across laboratories and galaxies, we will see what they disclose, without exhausting what they still conceal. Imagine a single photon leaving a distant galaxy, long before Earth had oceans or even a stable sky. In a crowded stellar nursery, an electron drops between atomic energy levels and releases one precise unit of light. It slips free from an atom, threads past dust grains that would rather swallow it, and escapes the thin gas that glows in ultraviolet. The photon enters open space, where empty still means fields, radiation, and the faint pull of gravity. For billions of years, it travels through expanding darkness, never slowing, never tiring, never taking a detour in the ordinary sense. It crosses regions where galaxies are still assembling, where black holes flare briefly, and where the background glow of the universe hums at microwave wavelengths. Then, in a quiet lab, it ends as a click in a detector. A photomultiplier flashes, a superconducting sensor warms by a whisper, or a silicon pixel releases a tiny cascade of charge, one event, localized and final. The thought seems simple, almost soothing, until the obvious question appears. What happened to that photon along the way, when no one watched, measured, or recorded its passage? Did it move like a tiny bullet on a definite path through the void, tracing a single line across cosmic time? Or did it spread like a wave across many possible routes, then choose one at the end? Light is the most familiar thing we experience without touching. It wakes us, warms us, guides our eyes, and sets the rhythm of days with a reliability that feels almost moral. Yet physics treats light as an object with rules that resist everyday intuition. The photon is common in experience and strange in concept, and that mismatch is where modern physics begins to feel like philosophy. This chapter begins with that tension and holds it gently. We're not racing for answers, and we are not trying to crush mystery into a slogan. We are building clarity slowly, one careful idea at a time, until the strangeness becomes precise. The goal is understanding without losing the sense of wonder, because wonder is often the mind noticing a real boundary. The central question is simple to ask and hard to finish. What is a photon, really? And why does light obey rules unlike anything else we know? To start, we define the photon in the most practical way we know. A photon is the smallest discrete packet of electromagnetic energy we can exchange with matter, as far as experiments can currently resolve. When atoms emit light, they do not leak energy smoothly like steam from a kettle. They trade energy in chunks, and those chunks arrive as individual detection events that can be counted, timed, and correlated. That operational definition is reliable, but it is not the whole story. Modern physics adds a deeper layer that changes how we picture the photon, especially when we ask what exists between interactions. In quantum field theory, the electromagnetic field fills space everywhere, even in perfect darkness. A photon is an excitation of that field, a quantized ripple that can be created or absorbed when charged particles interact. This is why asking what the photon is doing between emission and detection becomes subtle. Fields are spread out, and measurements are local, and the bridge between them is probability rather than trajectory. We will keep returning to the same puzzle from different angles. Each angle will feel like a new rule, slightly unsettling at first, until the rules begin to fit into one consistent picture. 3 headline strangenesses guide the journey, and they are worth naming early. They are wave and particle behavior, massless momentum, and time that does not pass along light's path. First, wave. Particle duality is not a slogan, but an observed pattern. Light interferes like a wave and arrives like a particle, and neither description alone predicts everything we actually see. In a double-slit experiment, single photons build an interference pattern over time. Each photon lands as one dot, yet the dots accumulate into fringes that match the mathematics of waves. Visually, it is almost haunting. A blank screen, then a sparse sprinkle of points, then, slowly, bands of brightness and darkness emerging from apparent randomness. The pattern looks planned, even though each arrival seems like a coin toss. If we try to learn which slit the photon used, the interference fades. The act of gaining path information changes the statistics we observe, because the experimental setup now entangles the photon with a record of which way. This is not just a limitation of clumsy instruments. In quantum mechanics explained carefully, information is physical, and the possibility of distinguishing paths reshapes the probability amplitudes themselves. The photon is not simply a wave that sometimes pretends to be a particle. It is described by quantum amplitudes that predict probabilities, not hidden trajectories, and those amplitudes can add or cancel like ripples on water. That cancellation is the key to interference, and it is also the key to why what happened can be the wrong question. When multiple alternatives are indistinguishable, the theory does not assign a single history, only a combined amplitude. Second, the photon has no rest mass, yet it carries energy and momentum. It can push on matter, transfer recoil, and exert radiation pressure, even though it cannot be slowed into a resting state. We can see that push in delicate experiments where mirrors feel a tiny force from a laser beam. We can also see it in the wild, where dust in space drifts under starlight like pollen in a sunbeam. Solar sails work because light carries momentum, and momentum transfer does not require mass. A large reflective sheet in space can gain speed slowly, because each reflected photon changes direction and delivers a minute impulse. Comets grow tails because sunlight and solar wind apply steady pressure over time. The tail does not point behind the comet like smoke in air, it points away from the sun, revealing the direction of the force. In relativity, energy and momentum are linked to spacetime geometry. For a photon, the relation is different from massive objects, and the difference matters because the photon's energy is tied directly to its frequency. That link is encoded in a compact rule. Higher frequency light carries more energy per photon. It is why blue and ultraviolet photons can trigger chemical changes that red photons cannot, even when the red light is intense. Third, the photon follows a null path through spacetime. Along such a path, the proper time between emission and absorption is 0, which is a precise statement about geometry rather than a mystical claim. This does not mean the universe is timeless to us, or that clocks stop in space. It means there is no rest frame for light, and no valid clock that rides with it, ticking along as it goes. From our perspective, that photon can cross the observable universe, and we can label the journey in billions of years. From the structure of spacetime itself, the interval along its path is fundamentally unlike a massive journey. This is one place where speed of light explained becomes more than a number. The constant c is not merely how fast something happens to move, it is a conversion factor that stitches space and time into a single causal fabric. These three strangenesses are not separate curiosities. They are connected, and the connections are where the story becomes calming and deep because the rules stop feeling arbitrary. Before we descend into the details, we widen the view to the sky. Photons are not only lab events, they are the universe's main messengers, and nearly every astronomical image is a map of captured quanta. Almost everything we know about distant space arrives as light. Starlight carries chemical fingerprints, temperatures, motions, and magnetic fields, because atoms and ions imprint specific patterns on spectra. A spectrum is not just a rainbow, it is a barcode of absorption and emission lines, each line tied to quantized electron transitions, and each shift in position revealing motion through the Doppler effect. When we say a star is rich in iron or poor in lithium, we are reading those lines. When we say a galaxy is rotating, we are watching the lines tilt and split across its disk. The cosmic microwave background is a sea of ancient photons. They last scattered when the universe cooled enough for atoms to form, and they still fill space today as a nearly uniform glow. Before that moment, the early cosmos was a hot plasma where electrons and nuclei constantly scattered light. As the universe expanded and cooled, electrons combined with nuclei recombination, and photons finally streamed freely. Those CMB photons are a photograph of an early time, stretched by expansion into microwaves. Their tiny variations map the seeds of galaxies, showing where matter was slightly denser and gravity had a head start. On screen, those variations look like soft mottling on an oval sky map, a delicate speckle pattern that seems almost like noise. Yet that noise is structure, and structure is destiny, written into temperature differences of mere microkelvin. Gravitational lensing bends light around mass, turning galaxies into arcs and rings. Photons trace spacetime curvature, and curvature reveals hidden matter, including the dark matter we cannot see directly. The visual is unmistakable, a bright arc wrapped around a cluster, a near-perfect Einstein ring around a distant galaxy, and multiple mirrored images where there should be only one. It is geometry made visible, with light as the chalk. Redshift is another photon record, written into wavelength. As space expands, photon wavelengths stretch, and that stretching becomes a measure of cosmic history and distance on the largest scales. This is not the same as a simple Doppler shift from motion through space. It is the stretching of space itself, carrying the photon's wave pattern outward so that crests arrive farther apart than when they left. Without photons, the universe would be almost unknowable to us. We could feel gravity and detect particles nearby, but the deep sky would be silent, because most cosmic events announce themselves first in light. So the photon is both a physical object and an information carrier. It is how the universe tells us what it is, and how it became this way, from stellar interiors to the edge of the observable horizon. That is why the question matters beyond curiosity. If we misunderstand photons, we misunderstand measurement, fields, and the geometry of spacetime, and we risk building intuition on the wrong foundation. Now we return to the single photon in our thought experiment. It left a galaxy when Earth was young, and it arrived as one count in a detector, with no visible record of the in-between. Between those endpoints, what is the right description? The answer depends on what we mean by description, and what we are allowed to ask, because physics is partly a theory of what can be operationally distinguished. In classical physics, light is an electromagnetic wave. It has frequency, wavelength, polarization, and it spreads smoothly through space as oscillating electric and magnetic fields lock together. That picture was not invented casually. It was forged in the 19th century, when Maxwell unified electricity and magnetism and discovered that changing fields propagate as waves at a speed matching measured light. Classical waves explain reflection, refraction, diffraction, and interference with elegant precision. They also predict continuous energy flow, like water in a stream, where you can always take a smaller cup and still collect some. But nature does not always deliver energy continuously. Photoelectric emission happens only when light frequency is high enough, even if intensity is low, and below a threshold frequency no electrons are ejected at all. That discontinuity forced a new idea. Light interacts in quanta, and the quantum is tied to frequency through Planck's constant, a tiny number that sets the scale of granularity. Historically, Planck introduced quantization reluctantly, as a mathematical fix for blackbody radiation. Einstein then took the step that felt almost heretical. He treated light itself as quantized, and the photon concept began to harden. Quantum mechanics explained why energy exchange is granular. It also introduced a new kind of description, where outcomes are probabilistic and measurement is central, because the theory predicts distributions rather than single certainties. This is where photon explained can mislead if we're not careful. The photon is not a miniature billiard ball, but neither is it a mere smear of wave energy, because experiments demand both discreteness and interference. Relativity arrived with its own revolution. It unified space and time, fixed the speed of light, and replaced absolute simultaneity with spacetime structure, where different observers slice time differently. The speed limit is not an engineering constraint. It is a statement about causality, about which events can influence which, and light sits exactly on that boundary, defining the edges of what can be connected. When quantum ideas meet relativity, the photon becomes even stranger and more constrained. It must always move at c in vacuum, and it cannot be brought to rest, so it never has the kind of here that massive objects can claim. Modern quantum field theory goes further by treating particles as field excitations. In that view, photons are not tiny beads, but quantized modes of a field, and their interactions arise from how fields couple. The field picture helps explain why photons can be created and destroyed. It also clarifies why counting photons is counting energy exchange, not tracking a little object, because the number of excitations can change as interactions occur. Still, the field picture does not erase the mystery of measurement. A field can be spread out, yet a detector registers a localized event, and the transition from spread out amplitude to single click is where interpretation enters. So we will proceed with care and with the right kind of patience. This is quantum mechanics explained in a way that keeps the edges soft, while still respecting the hard constraints of experiment. We will ask what is a photon, and we will not pretend the answer is a single metaphor. We will also touch speed of light explained, without turning it into a race, because the deeper point is geometry and invariance. The story arc of this documentary is already visible from here. We begin with ancient intuitions about vision and fire, then move to classical waves and Maxwell, when light became a field rather than a substance. We then meet the quantum discontinuity through Planck and Einstein, and the experimental puzzles that followed, where detectors clicked one by one even as interference demanded waves. Next comes relativity's spacetime, where light defines causal structure. In that framework, the photon is not merely travelling through space, it is tracing the boundary of what can happen next. From there, we step into the modern QFT picture, where photons are excitations and interactions are exchanges. Finally, we return to cosmology, where photons map expansion and curvature, and where the oldest light still surrounds us. Each step will answer one question and raise a sharper one. The purpose is not to make light ordinary, but to make its strangeness intelligible, so that mystery becomes a well-lit room rather than a fog. For now, keep the opening thought experiment close. A photon leaves, a photon arrives, and the universe in between is not empty, even when it looks like darkness. Space expands, gravity bends paths, and quantum rules limit what can be said about unmeasured histories. The photon is shaped by all of it, and our language must be shaped as well. When you picture that long journey, ask a quieter question beneath the obvious one. Is the photon a thing that persists, or is it better understood as a relationship between an emission and an absorption, connected by the electromagnetic field? In the next chapter, we start at the beginning of our ideas about light. We trace how familiar glow became unfamiliar rules, and why the shift was unavoidable once experiments began to count what eyes only blended. On-screen and end slate tags appear quietly at the end. We begin before the photon is even imaginable, when light is only experience and metaphor, and when language reaches for comparisons because measurement has not arrived yet. The central question still waits in the background, patient and unresolved. What is a photon, really? And why does light refuse ordinary rules? For most of human history, seeing feels active rather than passive, because attention seems to travel outward and land on things. The eye seems to reach outward, because concentration feels like a beam that can be aimed. In darkness, vision fails, so it seems the eye's fire has dimmed or withdrawn. That intuition is not childish. It is a reasonable inference from lived sensation, especially when the mechanics of eyes are unknown and anatomy is mostly guesswork. When you turn your head, the world snaps into clarity, and it feels like an act of will. When you close your eyes, the world disappears, and the mind blames the observer rather than the environment. Even the body encourages the illusion of action, because the eye muscles move with purpose, and the pupil visibly changes size. The pupils widening in dim rooms looks like a searching gesture, as if the eye is trying harder. Yet the physical truth is quieter. The pupil is a variable aperture, regulating how much light enters. It does this automatically, tightening in bright conditions and relaxing in low light to protect delicate cells. One ancient answer is extramission, the idea that the eyes emit rays that touch objects and return knowledge. It fits the feeling of looking, and it fits the geometry of pointing, because gaze has a direction. In this view, vision resembles a kind of probing, like a hand extended into space. The line of sight becomes a literal line, an imagined filament connecting observer and world. Extramission also harmonizes with older ideas about fire and spirit, where inner vitality could be imagined as literally luminous. The eyes shine in animals at night, and polished surfaces flash back light, so emission seems plausible. Even the language of casting a glance suggests something thrown outward. The gaze feels like agency, and agency is easy to mistake for a physical beam. Some versions of extramission try to sound practical rather than mystical, proposing that the eye sends out a subtle, invisible substance. That substance could be imagined as thin filaments, or as rays that spread in a cone. Once you picture a cone, you can picture why close objects feel more of it than distant ones. You can also picture why a narrow gaze might seem sharper, as if tightening the cone increases precision. Another answer is intromission, the idea that something from the world enters the eye, carrying form and colour. It fits the fact that bright light can overwhelm and damage sight, as if an external force is arriving. It also fits the way shadows appear to steal visibility by removing illumination. In this picture, darkness is not a failure of will, it is a lack of incoming signal. Intromission makes the environment responsible for vision, and it makes light a messenger rather than a tool. If something enters the eye, then the eye must be structured to receive it, focus it, and translate it. That invites questions about transparency, lenses, and the strange dark chamber of the skull. It also invites a practical question. What part of the eye actually knows the light has arrived? We now know that the retina is a sheet of light-sensitive cells, and that the optic nerve carries signals rather than images. Photoreceptors convert photons into electrical changes, and those changes are processed by layered neural circuits before the brain ever sees anything. Yet even without that knowledge, the intromission picture has a practical flavour. It treats light as a physical cause, and it implies that seeing depends on conditions outside the observer. Both models feel reasonable because they match different parts of experience, and because neither requires invisible machinery. We aim our gaze like a tool, yet we also depend on external illumination that we cannot summon at will. Early thinkers tried to reconcile these instincts with simple physical pictures, using analogy as their laboratory. The arguments are not idle, because they shape what counts as evidence in the first place. Greek philosophers argue over whether sight is a kind of touch at distance, or something more ethereal and immediate. Some propose a medium between eye and object that can be disturbed, like air that carries influence. Others treat vision as a direct line of influence, as though space itself transmits intention. Behind the words is a deeper problem. How can causation cross empty space without a carrier? The debate is not only about optics, it is about causality and contact, and about how knowledge can cross a gap. If vision is touch, what is being touched, and how does it avoid slowing down? If vision is emission, why does it not illuminate darkness, and why do we not see through walls? The questions sound naive, yet they press directly on what any physical theory must eventually answer. There is also a social reality behind the debate, because philosophy is competing with craft and medicine. Glassmakers, metalworkers, and artists know practical tricks of reflection and glare. Physicians observe injuries and cataracts, and they notice that the eye is vulnerable to what enters it. Even without microscopes, lived observation keeps whispering that the eye is not an invincible projector. Then geometry enters, and light becomes a set of rules rather than a story. Euclid describes rays as straight lines in space, building an optics of angles and sightlines. He does not need to decide what rays are made of because the mathematics works without a substance. That restraint is powerful, prediction arrives before ontology, and it changes the tone of inquiry. In Euclid's optics, the key fact is direction, and direction can be drawn with a ruler. If light travels in straight lines, then apparent size and perspective become calculable, even when distance is unknown. The world becomes measurable through angles, and measurement becomes a new kind of certainty. A line on a page begins to stand in for a path in space. We can picture the scene, a stylus scratching lines across wax, triangles forming between eye, object, and horizon. A tower shrinks as it recedes, not because it changes, but because the angles narrow. The geometry turns perception into a diagram, and the diagram begins to predict perception. In the quiet authority of the construction, the senses are invited to obey. This is also a subtle change in authority, because the diagram can outvote intuition. A well-drawn construction tells you what must be true, even if it feels strange. In that sense, optics becomes one of the earliest places where mathematics starts to discipline the senses. It is an early rehearsal for modern physics, where equations often speak before experience catches up. Reflection becomes a calm certainty, and it becomes teachable with a single clean rule. The angle of incidence equals the angle of reflection, and the mirror behaves like a disciplined surface obeying symmetry. The law feels almost moral, an orderly reply to a ray's approach. It implies that nature can be trusted to repeat itself with exactness. That rule does more than explain mirrors. It explains why polished metal can act like a window into another direction. It also explains why a small tilt can redirect a bright glint across a room. In visual terms, a mirror becomes a machine for steering light with precision. The world's brightness can be aimed, redirected, and controlled without ever touching the source. We can linger on the visual mechanics because they are simple and hypnotic. A ray approaches, a normal line stands like an invisible plum, and the outgoing ray leaves with matching dignity. The mirror does not store the light, and it does not hesitate. Its response is immediate. That immediacy quietly suggests that light's interaction with matter is fast, local, and rule-bound. This is a crucial shift for our documentary's arc, because usefulness separates from ontology. A theory can be powerful without being complete, and a model can predict without revealing essence. Light can be treated as lines, even if its substance remains unknown, and that is a new kind of intellectual restraint. The ray becomes a tool, an abstraction that works even while the underlying reality stays hidden. Simple demonstrations make this feel inevitable, and they look almost magical when staged in a darkened room. A mirror redirects a beam without delay, and the reflected spot slides across a wall with perfect obedience. A pinhole projects an inverted image that seems to prove straight paths, as though light were a rain of tiny arrows. The room itself becomes a laboratory, and the wall becomes a screen for invisible geometry. The pinhole image is especially persuasive, because it turns the world into a picture with no lens and no artistry. It shows that each point on an object maps to a point on a screen, and that the mapping is stable. It suggests that light carries spatial information by travelling along distinct directions, not by smearing through space. Even the inversion becomes a lesson. Top rays cross bottom rays at the aperture, and the world flips. We can linger on the visual. A bright outdoor scene becomes a dim, crisp miniature inside a dark box. Trees hang upside down, clouds drift in reverse, and people walk along the ceiling. The effect is quiet and undeniable, an image formed by geometry alone. The box feels like a confession from nature, admitting that straight paths are real. If we move closer, we see why the image is dim, and the reason is physical rather than mystical. A small hole admits only a narrow bundle of rays from each point in the scene. Sharpness improves as the hole shrinks, but brightness collapses, and the trade-off hints at deeper rules. Even here, the future is foreshadowed. Nature often demands a price for precision, Yet the early models still leave a gap that geometry cannot close. If rays are emitted by eyes, why do we not see in darkness? And why does staring not brighten a room? If rays come from objects, what exactly is leaving them? And how can a stone send anything at all? The more successful the diagrams become, the more urgent the what behind the lines feels. The story tightens when experiment becomes a discipline rather than an occasional trick, and when observation is treated as a judge. In the Islamic Golden Age, Ibn al-Haytham insists on testing claims, even when the claims are ancient and respected. He treats optics as a physical science, and he insists that light must obey rules that can be checked. His approach is methodological, an insistence that nature, not tradition, gets the final word. This matters historically because it is a methodological statement, not only an optical one. Alhazen writes with an insistence on controlled conditions, careful description, and repeatable outcomes. He is not satisfied with plausibility, because plausibility can be a mirror that flatters the mind. In his hands, optics becomes less like rhetoric, and more like engineering for truth. Alhazen rejects extramission as a primary mechanism, not by insult but by argument and demonstration. He notes that intense light injures the eye, which makes more sense if something enters rather than exits. He argues that light travels from luminous sources to objects, then to the eye, and that vision depends on incoming light. He also emphasizes that the eye cannot reasonably emit rays strong enough to explain the brightness of the sun. He also treats the eye as an optical instrument, with parts that can be described rather than enchanted. The cornea and lens refract incoming rays, and the pupil limits them, shaping what reaches the inner surface. In plain terms, the eye is a camera made of living tissue. The eye's focusing is not willpower. It is refraction and curvature, tuned by biology. His camera obscura work makes the point concrete, and it is a turning point because it removes the observer from the mechanism. Light from a bright scene passes through a small aperture, and it forms a coherent image without any eye present. The image appears whether anyone is watching, and that fact is quietly revolutionary. It suggests that seeing begins as physics, long before it becomes perception. We can picture his setup in a sunlit courtyard, with a darkened room beside it and a single pinhole in a shutter. Outside, motion is loud and ordinary, but inside the image is ghostly and precise. The world writes itself onto a surface and no mind is required. The silence of the dark room makes the conclusion feel heavier. Light does not need us to exist. This is an early empirical pivot, and it changes the direction of explanation. The eye becomes a receiver, not a projector, and the world becomes the source of the signal. The geometry remains, but the direction of causality flips, and the flip matters. It also sets a precedent. When intuition conflicts with a device that records, the device often wins. Alhazen also emphasizes that light has a finite propagation in a medium, and he treats its behavior as something that can be analyzed. He discusses refraction and the bending of rays at boundaries, where air meets water or glass meets air. He treats these as lawful effects, not mystical transformations, and he looks for consistent relationships. The boundary becomes a place where hidden rules reveal themselves through visible distortions. Refraction, in particular, invites a deeper question, because bending implies a change in speed or a change in direction rule. A stick in water appears broken, and a coin in a cup seems to rise when water is poured in. These are not mere illusions, they are clues that light's path depends on the material it passes through. The world is not only lit, it is optically textured, with each substance shaping light in its own way. We now speak of refractive index, a number that summarizes how strongly a material slows light compared with vacuum. That number is not arbitrary, because it emerges from how electromagnetic fields polarize atoms and molecules. In simple language, the material briefly borrows the wave's energy and returns it delayed. The delay accumulates across countless interactions, and the macroscopic result is a slower effective speed. Still, even with intromission, light remains ambiguous, and the ambiguity becomes more pressing as optics becomes more successful. Is it a substance streaming through space, like fine dust or invisible fluid? Is it a disturbance travelling through something else, like a ripple through air? The question is not cosmetic. Different answers imply different mechanisms for reflection, refraction, and speed. As centuries pass, the practical success of geometrical optics grows, and it becomes part of everyday craft. Lenses focus, telescopes extend sight, and microscopes reveal hidden structure, turning tiny textures into landscapes. The straight-line model works until it does not, and the failures are as informative as the successes. Each new instrument is a stress test for whatever light really is. When a lens forms an image, it seems to tame light into obedience, compressing rays into a point and then spreading them again. Yet even in early instruments, fringes and blur appear at the edges and colours separate near bright boundaries. Those imperfections are not merely bad glass, they are messages from the underlying physics. They hint that light carries more structure than a simple line can hold. A deeper question begins to press, and it is the kind of question that turns philosophy into physics. If light is a physical thing, it should have a speed, even if that speed is enormous. If it has a speed, it should be measurable, at least in principle, by comparing clocks and distances. The challenge is not conceptual, it is technological, because the universe hides fast things behind small delays. For a long time, the speed of light seems either infinite or too large to matter, because human-scale events show no delay. Everyday experience offers no pause between a candle and its glow. Lightning and thunder separate, but light appears immediate, arriving before the mind can count. The eye and brain also integrate over time, smoothing tiny delays into a single impression. Even attempts to measure it on Earth face a brutal problem, because the expected delay is tiny. Over a kilometre, light takes only a few microseconds, and early clocks cannot resolve that. To catch light in the act of travelling, you need either extraordinary timing or extraordinary distance. The solution will come from the sky, where distance is abundant and periodic motion supplies a natural clock. Then astronomy provides a clock large enough to notice, and the solar system becomes an instrument. Ulrema studies the eclipses of Io, a moon of Jupiter, watching it slip into Jupiter's shadow with regularity. The timing shifts depending on Earth's position, and the shift is systematic rather than random. The key is repetition, many eclipses, many nights, and a pattern that refuses to be dismissed. The scene is almost cinematic, because the measurement is made with patience rather than machinery. Night after night, Jupiter hangs like a bright coin, and Io's disappearance is a tiny punctuation mark. Rumour is not timing a flash in a lab. He is timing a rhythm in the heavens. He is listening for a delay in a cosmic metronome, and the metronome is millions of kilometres away. When Earth moves away from Jupiter, Io's eclipses appear late, as though the signal is lagging behind the schedule. When Earth moves toward Jupiter, they appear early, as though the signal has less distance to cross. The simplest explanation is a finite travel time for light, and simplicity matters when data repeats. The conclusion is not dramatic in a single night, but it becomes unavoidable over months. In 1686, Rumour estimates that light takes minutes to cross Earth's orbital diameter, using the accumulated drift in eclipse times. The number is rough, because distances in the solar system are not yet known with modern precision. The implication is sharp, because it turns immediacy into travel. Light is no longer a mystical instant, it is a messenger with a schedule. This moment adds scale and wonder to the narrative, because it converts space into time. A phenomenon once treated as instantaneous now has a measurable delay, and the delay is written into the motion of planets. The universe becomes a laboratory for timing, and the laboratory is unimaginably large. It also changes how we imagine observation itself. When we look far away, we look back in time. Finite speed also changes what a theory must explain, because propagation implies a mechanism. If light takes time to move, it resembles a travelling entity that carries influence from place to place. That entity could be a stream of particles, each one moving along a trajectory, or it could be a moving wave spreading through a substrate. Either way, light becomes a traveller, and travellers invite questions about what they're made of. The next conflict becomes famous because it is productive, and because it forces clarity about what counts as explanation. Newton argues for corpuscles of light, and he does so with the confidence of a mechanics that has already conquered the planets. Huygens argues for waves propagating through a medium, and he does so with a geometry of wavefronts that can also predict paths. The disagreement is not a mere preference, it is a clash of metaphors that each claim to be physical. Newton's corpuscles fit his broader mechanical worldview, where forces act on bodies and bodies trace curves. Particles move in straight lines, reflect like bouncing balls, and refract by forces near surfaces. The model feels like physics that can be pictured, and picturing is persuasive. It also aligns with the sharpness of shadows, where light seems to respect edges rather than seep around them. In Newton's era, matter is understood as something with mass, momentum, and impact, so particles feel like the responsible choice. A particle can carry energy without needing a carrier, and it can explain sharp boundaries. It also fits a world where collisions and pushes explain almost everything else. If nature is a machine of impacts, then light should be a kind of projectile. In the corpuscular view, a surface is not only a boundary, it is a region that can pull or push the corpuscles. Refraction becomes a kind of bending by attraction, like a comet deflected near a planet. The ray diagram remains, but the ray now stands for a stream of tiny projectiles. The simplicity is seductive: straight lines, sudden turns, and rules that resemble mechanics. Huygens wave theory begins from a different intuition, and it treats light as a process rather than a fleet. Each point on a wavefront acts as a source of secondary wavelets, spreading outward in all directions. The new wavefront is the envelope of those wavelets, and the envelope becomes the next moment in time. In this view, the ray is not fundamental. It is a convenient arrow drawn after the fact. That construction is more than a metaphor, because it can be drawn and used to calculate refraction and reflection. A wavefront striking a boundary changes speed, and the change in speed tilts the wavefront. The ray, in this view, is a perpendicular to the wavefront, a convenient arrow that hides a broader spread. The picture is less like billiards and more like a marching line that changes pace. Both theories can reproduce key optical laws, which is why the argument lasts so long. Reflection is straightforward in either picture, because symmetry at a surface produces equal angles. Refraction can be explained by changing speed in a medium, though the details differ, and the predicted speeds become decisive. The fight becomes quantitative, because numbers can embarrass even elegant intuitions. The disagreement is not only philosophical, because it produces opposite quantitative claims. Newton predicts that light should travel faster in denser media, because corpuscles are pulled in and accelerate. Huygens predicts the opposite, because waves slow down in denser media, as sound slows in some materials. The difference is subtle in concept but sharp in consequence. One measurement can choose between world views. Experiments eventually favour Huygens on that point, but the road is not immediate because measuring light's speed in materials is difficult. Foucault and others measure light's speed in water and find it slower than in air, using rotating mirrors and careful timing. The wave view gains ground because it wins where numbers matter. The victory is not rhetorical, it is written in measured delays. Yet Newton's authority and the success of his mechanics keep corpuscles alive, and not merely out of loyalty. The corpuscle picture also seems to match sharp shadows and straight rays, because particles do not naturally spread. It feels compatible with the pinhole image, where the world maps cleanly through a small hole. Even when waves are persuasive, the particle intuition keeps returning. Stubborn, familiar, and sometimes useful. The 19th century brings evidence that is hard to ignore, and it arrives in patterns rather than arguments. Thomas Young performs the double-slit experiment with light, letting it pass through two narrow openings. Bright and dark fringes appear where particles would only add, and the darkness is the scandal. The experiment is simple to describe, yet it rearranges the logic of what light can be. Interference demands superposition, which is a wave idea stated in plain language. Two paths can combine to reinforce or cancel, producing stripes of brightness and stripes of absence. The pattern depends on wavelength, not on any simple collision rule, and it persists even when the setup is refined. Change the slit spacing, and the fringes shift, like a ruler made of light. Visually, the screen becomes a kind of fingerprint for light, and the fingerprint is periodic. Bands of illumination march across the surface, then fade into bands of shadow with equal discipline. It is as if light is arguing with itself, arriving by two routes and negotiating what will be seen. The apparatus feels almost like a courtroom, and the fringes feel like testimony. The darkness in the pattern is especially provocative, because it is not a lack of light sources, it is a structured absence, appearing exactly where the wave peaks and troughs cancel. How can two somethings combine to make nothing, unless the something is an oscillation with phase? The question forces a new kind of realism. Phase is not a story, it is a measurable ingredient. Fresnel extends this into diffraction theory, and the extension is mathematical rather than rhetorical. Light bends around edges and through apertures in a way that matches wave mathematics, producing fringes near shadows. the straight-line ray becomes an approximation, not a foundation, and the approximation has limits that can be predicted. The edge of a shadow becomes a place where the wave reveals itself, like a signature at the margin. Diffraction also explains why perfect sharpness is impossible, even with ideal lenses, because apertures impose wave constraints. A point of light cannot be focused to an infinitely small point, because a wave passing through a finite opening spreads. The idea that geometry is enough begins to soften, replaced by the idea that geometry is a high-frequency shortcut. The crisp ray is still useful, but it is no longer the whole truth. Polarization adds another constraint, and it is a constraint that feels almost tactile. Light can be filtered by orientation, and certain reflections produce polarized beams that behave differently through crystals. This suggests that light's oscillations have direction, not merely magnitude, and direction is a strong clue. The wave is not just up and down in brightness, it has an internal alignment that can be selected and rotated. Longitudinal waves like sound do not naturally explain polarization, because their vibrations align with the direction of travel. Transverse waves do because their vibrations can point sideways and be selected by an oriented filter. If light is a wave, it seems to be a transverse wave, and that implies a medium with unusual properties. The medium would need to resist shear like a solid, yet remain invisible and frictionless, an uncomfortable combination. At this stage, the story seems to settle, and the settlement has the calm of a solved puzzle. Light is a wave, and waves require a medium, at least in the classical imagination. The medium becomes the ether, a comforting substance that fills space, even where air is absent. It is a placeholder for common sense, a way to make waving feel mechanically respectable. The ether solves a psychological problem as much as a technical one, because waves without a carrier feel impossible in older physics. Water waves need water, and sound waves need air, so a wave in emptiness seems like motion without matter. The ether becomes the unseen something that makes waving respectable. It also becomes a promise. If we can find the medium, we can finally say what is oscillating. 19th century physics also wants ether for precision, because electromagnetism is becoming a unified theory. If light is an electromagnetic wave, then electric and magnetic fields must be something that can oscillate and store energy. The ether becomes the stage on which fields perform, giving them a place to be. The language of field is still young, and the ether offers an older kind of comfort, substance. The ether is imagined as rigid enough to support high-frequency transverse waves because light's frequency is immense. It must also be subtle enough to offer no resistance to planets, which move without drag through space. It must be everywhere, yet almost undetectable, and those requirements strain intuition. The more carefully it is specified, the less it resembles any known material. This is the tension that builds quietly, and it builds because the ether is tuned to satisfy contradictory demands. It is a medium with properties designed to avoid being noticed, yet it must be real enough to carry the fastest waves. The more carefully it is described, the more ghost-like it becomes. At some point, you have to ask whether the medium is explaining light, or merely protecting an old habit of thought. As measurements improve, physicists look for the ether wind, and the search is straightforward in principle. If Earth moves through the ether, then the speed of light should differ with direction. Like swimming upstream or downstream, the difference should be small but measurable, and interferometry can measure small differences. The experiment is a wager. If the medium is real, motion through it should leave a trace. Michelson and Morley build an interferometer to detect that difference, and the device is a triumph of precision craft. They split a beam, send light along perpendicular arms, and recombine it to produce interference fringes. A shift in fringes would reveal motion through ether, because the travel times would change. The instrument is sensitive not to brightness, but to phase, timing encoded as pattern. In visual terms, the apparatus is almost ceremonial. Mirrors aligned, beams crossing, a pattern of light and dark held steady like a ruler. The fringes are not a picture of an object, but a picture of timing. If the ether wind exists, the picture should slide as the instrument rotates with Earth. The rotation becomes a slow, deliberate question posed to space itself. The result is a null, and the null is unsettling because it is not ambiguous. The expected fringe shift does not appear, and repeating and refining the experiment does not rescue the ether wind. The pattern stays stubbornly put, as though space refuses to reveal any preferred flow. It is a quiet kind of shock. No explosion, just the absence of the expected signal. This is not an immediate death blow because scientists are trained to protect successful frameworks. Ad hoc fixes appear, including length contraction and partial dragging, each designed to hide the wind while keeping the medium. Each fix preserves the ether by making it harder to detect, and the theory begins to feel defensive. When a theory survives by becoming untestable, its strength starts to look like fragility. The narrative tension rises because the wave picture is working too well, and because the evidence for waves is rich. Interference, diffraction, and polarization all point to waves, and the mathematics is elegant. Yet the medium that should carry waves refuses to show itself, and the refusal is now an experimental fact. The story becomes a paradox. The wave is visible, but the carrier is not. So we arrive at a strange question that feels almost like a riddle, and riddles are dangerous in physics. If there is no detectable ether wind, what is waving, and what does wave even mean without a substance? If light is a wave, what is the thing that oscillates, and where is the energy stored? The question is both technical and philosophical, because it asks what counts as a thing in physics. This is where the documentary's hook returns in a quieter form, because the mystery has matured. Light crosses vast distances with perfect regularity, and it does so through near vacuum where no classical medium is apparent. It seems to need no substance to push against, and yet it behaves like a wave with exquisite phase. The universe is filled with starlight, and the starlight arrives as if space itself knows how to transmit order. The stage is set for a new kind of explanation, and it will sound radical only because older habits are strong. Maxwell's equations will soon describe electromagnetic fields as self-propagating, where changes in electric fields generate magnetic fields and vice versa. The wave will be in the field itself, not in a mechanical medium, and the carrier will be the structure of the equations. In that framework, the speed of light is not an accident. It is built into the constants that relate electricity and magnetism. It is worth pausing on what that means in plain language because it is both abstract and concrete. A field assigns a value to every point in space, like a weather map assigns temperature and wind. If the field changes in time, those changes can move outward as a wave, no material required. The substance is not a hidden fluid, but a set of measurable quantities that can store energy and momentum. But even that classical triumph will not end the story, because success exposes new limits. As classical physics perfects waves, a new problem appears. Light exchanges energy with matter in discrete lumps, and the smooth continuity begins to fracture under careful measurement. The wave description remains powerful, yet it begins to look incomplete, like a map that captures coastlines but misses the tides. That final beat matters for our central question, because it reopens the door that waves seem to close. A particle of light once seemed unnecessary, even crude, like a retreat to old intuitions. Soon it will become unavoidable, and the word photon will enter the scene with a new kind of precision. The mystery deepens. How can light behave like a wave in space, yet arrive like counted events in matter? For now, we pause on the threshold, where the past is still visible behind us. Ancient vision theories gave us direction and geometry, turning sight into lines and angles. Wave optics gave us interference and polarization, turning light into a phenomenon of phase and superposition. The ether dream gave us a medium that could not be found, and the absence became its own evidence. Each step solved a problem, and each solution uncovered a sharper question. In the next chapter, the wave becomes a field, and the field becomes quantized, and the change will feel both inevitable and shocking. The calm certainty of continuous light begins to fracture into countable events, and the photon waits, still unnamed, but already casting its shadow forward. Light has behaved like a wave for so long that continuity feels like a promise, almost a moral expectation about how nature should distribute energy. Maxwell's fields spread smoothly through space, and the mathematics encourages a quiet confidence that energy is divisible without limit, like water poured into ever smaller cups. In that classical picture there is no smallest splash, only smaller and smaller ripples that still carry meaning. In the 19th century, that confidence was not naive because it was earned. Interference fringes, diffraction patterns, and polarization all spoke the language of the waves, and they spoke it with precision that engineers could trust. When a theory predicts the bending of light through a slit and the colours in a thin film, it feels complete. The wave model did not merely explain, it also built instruments, guided lenses, and made navigation and communication more reliable. But when physicists tried to heat matter and predict its glow, the promise broke. The break was not philosophical at first, because it arrived as a stubborn numerical mismatch between theory and measurement. It showed up as a curve that refused to fit, even when the apparatus was polished and the mathematics was elegant. In laboratories where temperature could be controlled and spectra could be recorded, nature kept returning the same uncooperative answer. A black body is an ideal emitter and absorber, a thought experiment object that helps isolate the essentials. In practice, it is modelled as a cavity, often a metal box, with a small hole that lets radiation leak out. Light that enters the hole bounces around, reflects many times, and is overwhelmingly likely to be absorbed. The hole behaves like a near-perfect black surface, not because it is painted black, but because geometry makes escape unlikely. Heat the cavity walls, and the hole shines with a spectrum that depends only on temperature. The surface material, the paint and the chemistry, become irrelevant, because the cavity forces the radiation toward equilibrium. In equilibrium, emission and absorption balance, and the radiation inside becomes a kind of thermal gas of electromagnetic waves. It is a gas with pressure, energy density, and a well-defined temperature, even though it is made of light. This spectrum became a benchmark because it ignored almost everything messy. It was pure thermodynamics welded to electromagnetism, and that combination should have been a triumph for classical physics. If any problem should yield to 19th century methods, it was this one. The blackbody curve was also practical because it anchored temperature measurement and calibration in a repeatable physical standard. Visually, the blackbody curve is simple and strangely beautiful. As temperature rises, the glow shifts from dull red to white hot, and then toward bluish brilliance. The curve rises from near zero, swells to a single peak, and then tapers off into a thin tail. On screen, the peak slides left as the object heats, like a moving hill that drifts toward shorter wavelengths, while the overall area under the curve grows. Classical physics treated the cavity as a box of standing electromagnetic waves. Each allowed mode was like a harmonic on a string, with nodes and antinodes fixed by the cavity's geometry. The field could vibrate at many frequencies, and the cavity's size determined which frequencies were permitted. In 3 dimensions, those patterns are richer than a string's simple harmonics, because waves can fit along many directions at once. To count the energy, physicists counted the modes. For each frequency range, there are many ways to fit a wave pattern into the volume, and that number grows rapidly at shorter wavelengths. In 3 dimensions, the density of modes rises roughly with the square of the frequency, which becomes decisive. The counting is geometric, like packing ever smaller tiles into the same floor area, and the small tiles proliferate. Then equipartition entered, the rule that thermal energy spreads evenly across degrees of freedom in equilibrium. In its simplest form, each quadratic degree of freedom gets an average energy of about kT. That idea had already explained why gases have predictable heat capacities, and it felt like a universal law. It was the kind of principle physicists loved, because it turned microscopic chaos into a clean, macroscopic number. The assumption sounded modest, almost inevitable, because it worked so often. It treated energy as continuous and shareable, and it matched much of 19th century intuition about smooth variation. If a system can store energy in a degree of freedom, why would temperature not feed it evenly? In classical mechanics, nothing prevents a degree of freedom from holding an arbitrarily small amount, so the equal sharing seems natural. But the number of modes rises sharply with frequency, because shorter wavelengths fit more patterns inside the cavity. As frequency climbs, the count of available modes explodes, filling the spectrum with ever more slots to hold energy. The cavity becomes, in theory, an infinite warehouse of high-frequency possibilities. The classical bookkeeping keeps opening new shelves, and it never finds a reason to stop. If each of those modes gets kT, the total energy at high frequency diverges. The predicted spectrum shoots upward into the ultraviolet, then keeps climbing without bound, as if the cavity were a furnace that cannot stop producing ever hotter light. The mathematics does not merely overshoot the data, it runs away. The divergence is not a technical annoyance because it implies a physical impossibility at ordinary temperatures. This was the ultraviolet catastrophe, a name that captures the mood more than the math. Classical theory predicted that warm objects should radiate infinite power at short wavelengths, which is not a small error but a logical collapse. If the prediction were true, a warm room would be lethal. Even a teacup would pour out an absurd torrent of invisible ultraviolet energy, and the world would not resemble itself. Nature did not do that, and the mismatch was not subtle. Real black-body curves rise, peak, and then fall, with the high-frequency tail suppressed in a way that instruments could map carefully. The experimental point sat calmly on a finite curve, while classical theory screamed upward. The calmness of the data is part of the drama, because it shows nature is not confused, only our assumptions are. The crisis was specific and sharp, because the failure happened where the assumption seemed most secure. A continuous wave theory plus equipartition produced an unphysical infinity, right where experiments were most reliable and reproducible. It was a failure of principle, not of craftsmanship. The catastrophe also hinted that classical statistical mechanics was being asked a question it could not answer honestly. The catastrophe mattered because it threatened the logic of thermal physics. If equipartition failed here, then the link between temperature and microscopic motion was incomplete, and perhaps conditional. It suggested that degrees of freedom might not all be equally available at a given temperature. Some modes, especially the high-frequency ones, seemed to be effectively frozen out, as if nature imposed a hidden access rule. It also mattered because it threatened the wave picture of light. If light energy can be distributed continuously among modes, why does the distribution refuse to follow the classical rule? The cavity was supposed to be the cleanest stage for waves, and yet the waves misbehaved. The failure landed at the intersection of two triumphs, Maxwell's electromagnetism and Boltzmann's statistical reasoning. At the turn of the century, Max Planck tried to rescue the curve without overthrowing physics. He wanted a derivation that kept Maxwell's waves and kept thermodynamics intact, because those pillars had earned deep trust. His goal was conservative, even if the result was not. In that era, revolution was not the desired aesthetic, and Planck did not set out to found a new worldview. Planck was working in a scientific culture that prized continuity. Discrete atoms were still debated in some circles, and the idea of discontinuous energy exchange felt like a regression. The safest move was to treat the problem as one of statistical bookkeeping, not ontology. The language of entropy and probability offered a way to adjust the counting without loudly rewriting the nature of light. Planck modelled the cavity walls as containing tiny oscillators that could exchange energy with the field. These oscillators were not atoms in a modern sense, but effective emitters and absorbers, little resonant systems coupled to the radiation. They were a bridge between matter and the electromagnetic field. In modern terms, they resemble charged degrees of freedom that can vibrate and radiate, trading energy with the cavity modes. He searched for a formula that matched the measured spectrum across all frequencies. The data demanded a specific shape, and the shape demanded a new assumption, because every classical attempt failed at the ultraviolet end. The curve itself became a kind of judge, accepting only one answer. The most striking demand was the rapid fall-off at high frequency, which classical equipartition simply could not justify. Planck's assumption was that the oscillators could not exchange arbitrary amounts of energy. They could only trade energy in discrete packets proportional to frequency, as if the oscillator's energy came in rungs rather than a smooth ramp. The exchange was quantized, even if the field remained wave-like. In the counting of microstates, those rungs matter, because they limit how energy can be distributed among oscillators. The rule was simple in form and radical in implication. The allowed energies came in steps of E equals h times nu, with h a new constant that had to be inferred from the data. A single symbol, introduced to fix a curve, would soon mark the boundary of a new physics. Planck's constant is small, but it is not optional, and its presence in the formula is a flag that classical continuity has been interrupted. Here nu is the oscillator frequency, and h is Planck's constant, a tiny number that sets the scale. When h is small, discreteness hides at everyday energies, which is why classical physics can feel so reliable. The grain is there, but it is usually too fine to notice. Only when we deal with microscopic energies or very high frequencies does the grain become visible, like pixels appearing when you zoom in too far. Planck did not initially claim that energy itself was fundamentally granular everywhere. He treated quantization as a constraint on exchange, a mathematical move to make counting work in the entropy calculation. In his own view, it was a formal trick that happened to succeed. He was trying to preserve continuity in the field, while quietly restricting how matter could trade with it. He introduced it reluctantly, almost apologetically, because it looked like a trick. Yet the trick produced the correct spectrum, including the suppressed ultraviolet tail that classical theory could not tame. The curve that refused to fit suddenly aligned with the measurements across the full range. What had been a crisis became a precise agreement, and that precision made the new constant impossible to ignore. In Planck's formula, low frequencies recover the classical result, and high frequencies are exponentially damped. That exponential factor is the quiet assassin of the catastrophe, because it makes high-frequency energy contributions rare. The theory stops feeding the ultraviolet warehouse. In plain terms, the high-frequency modes exist, but they are seldom populated at ordinary temperatures. The logic is statistical and unforgiving. If energy comes in chunks that grow with frequency, then high-frequency chunks are expensive at a given temperature, and most oscillators cannot afford them. Thermal equilibrium becomes a budget and the ultraviolet is overpriced. The distribution is no longer a smooth spread across infinitely many shelves, because the price per item rises with frequency. A warm cavity can afford many low-frequency quanta, but it cannot afford many ultraviolet quanta. The spectrum peaks where the trade-off between mode density and quantum cost balances, producing a maximum that shifts with temperature. That shifting peak is why hotter objects look bluer. The peak's motion is not arbitrary. It encodes a quantitative relation between temperature and wavelength that later becomes a tool of astrophysics. If we visualize the cavity as a crowded concert hall of modes, Planck's rule changes who gets tickets. Low-frequency seats are cheap and fill easily, while high-frequency seats are expensive and mostly empty. The audience distribution becomes the spectrum we observe. On screen, the hall could be shown with bright clusters in the low-frequency sections, fading to sparse, isolated lights in the ultraviolet balconies. Planck had fixed the curve, but the fix carried a splinter. If oscillators exchange energy in indivisible units, then continuity is not a universal principle, and the old intuition becomes conditional. The smoothness of Maxwell's equations might still be true, yet incomplete. A theory can be correct in its propagation rules, and still be incomplete in its rules for exchange. The central question sharpens in the background. What is a photon really, if the field is continuous, yet the exchange is quantized? Is the discreteness in matter, in radiation, or in the act of interaction itself? The question is not only metaphysical, because it predicts what experiments should allow and what they should forbid. For a few years, the quantization could be treated as a property of matter, not of light. The field could remain a smooth wave, while walls behaved with discrete bookkeeping, like bankers forced to count in whole coins. That compromise was psychologically comfortable, and it delayed the deeper rupture. It also matched Planck's own cautious temperament, because it let him keep the wave picture intact in the space between interactions. Then a different experiment refused to stay inside that compromise. It involved light shining on metal, and electrons leaving the surface as if kicked, not warmed. The metal behaved less like a sponge soaking up wave energy, and more like a gate with a strict toll. The effect was dramatic because it turned illumination into an electrical event, a conversion that could be timed, measured, and repeated. The photoelectric effect was known as a phenomenon before it was understood as a crisis. Shine light on certain metals, and an electric current can flow in a circuit because electrons are liberated and collected. The effect could be demonstrated with simple apparatus, yet it resisted simple explanation. In the lab, one can imagine a clean metal plate in vacuum, a second electrode nearby, and a sensitive meter that twitches when light hits. The surprising part was not that light could liberate electrons. The surprising part was how the liberation depended on color and intensity, and how quickly the response occurred. The metal did not seem to charge up gradually, as a wave-based intuition might suggest. The immediacy matters because it suggests the energy arrives in a single decisive transaction, not as a slow transfer spread over time. Classical wave theory ties intensity to energy delivered per unit time and area. A brighter wave should carry more energy, regardless of its frequency, because amplitude sets energy density in the field. If the field is stronger, it should do more work. Frequency, in that view, changes the rhythm of oscillation, but not the basic ability to deliver energy if the amplitude is large enough. So the classical expectation was straightforward. If you increase intensity enough, even low-frequency light should eventually supply enough energy to eject electrons. The energy could accumulate in the electron, slowly building until escape becomes possible. It is the same intuition that says a gentle push can move a heavy object if you push long enough. You might expect a delay at low intensity, as electrons slowly accumulate energy from the wave. You might also expect the electron energy to grow with intensity, because a more intense wave should deliver more energy per unit time. These expectations are natural if energy is continuous and locally absorbable. A classical electron coupled to a continuous field should be able to drink from that field in arbitrarily small sips. Nature answered differently, and the answer was repeatable. Below a threshold frequency, no electrons are ejected, no matter how intense the light is, even if the beam is painfully bright. The metal remains stubbornly quiet, as though the wave were powerless. The threshold is sharp enough to feel like a rule, not a trend, and that sharpness is what makes it so instructive. Above that threshold, electrons are ejected promptly, even at low intensity. The response is essentially immediate on experimental timescales, which undermines the idea of slow accumulation. The metal behaves like a trigger, not a reservoir. If the light is allowed, the effect begins at once, and if the light is forbidden by color, it never begins. Increase intensity, and you get more electrons, but their maximum kinetic energy barely changes. The current rises because more electrons are emitted per second, yet the fastest electrons do not get faster. It is as if brightness controls quantity, while color controls quality. That separation of roles is a signature that the energy is arriving in standardized denominations. The maximum kinetic energy depends on frequency, not brightness. Blue and ultraviolet light produce more energetic electrons than red light, even when the red beam is stronger. The energy scale tracks the color in a way that feels almost like a ruler. The measurement can be made by applying a stopping voltage that just prevents the most energetic electrons from reaching the collector, turning electron energy into a directly readable electrical threshold. This is where the wave picture feels cornered. A wave spreads energy across space and time, and it does not naturally impose a hard frequency cutoff. A continuous field can be made arbitrarily intense, so why would it fail absolutely below some color? The cutoff suggests that something about the interaction is quantized, because a continuous reservoir should not have a strict minimum per event. If energy is continuous, then a sufficiently intense red wave should deliver enough energy to some electron eventually. Yet the experiments say there is a strict no, not a slow yes, and the strictness is what makes it unsettling. The metal seems to demand a minimum per interaction. It is as if the surface has a lock that only opens for keys with enough teeth, regardless of how many weak keys you bring. In 1905, Albert Einstein took Planck's hint and pushed it into the light itself. He proposed that light sometimes behaves as if it arrives in localized quanta, and that these quanta carry energy proportional to frequency. It was a conceptual leap that reinterpreted Planck's constant. Einstein's move also fit his broader style because he was willing to treat a successful formula as a clue about reality, not merely a computational device. Einstein's step was bolder than Planck's bookkeeping. Planck quantized exchange in matter, but Einstein quantized the radiation field as an emitter of packets, treating the light beam as granular at the point of interaction. The discreteness moved from the wall to the wave. In that shift, the coin values were no longer a property of the metal alone, but a property of the light itself. He suggested that a light beam is like a stream of energy quanta, each with energy E equals h nu. The frequency sets the energy per quantum, not the intensity, which is a profound reversal of classical emphasis. The color becomes the price of a single packet. In this view, a dim ultraviolet beam can still deliver high-energy packets, while an intense red beam delivers many low-energy packets. Intensity in this picture is the number of quanta arriving per second per area. Brighter light means more quanta, not bigger quanta, so it increases the rate of events rather than the energy per event. The beam becomes a rainstorm, not a rising tide. A heavier rain produces more splashes, but each drop still has the same size set by its frequency. Now the photoelectric rules become simple and almost mechanical. An electron absorbs one quantum, and if the quantum energy exceeds a binding cost, the electron escapes, like a ball that clears a wall only if it has enough speed. The interaction is all or nothing at the level of a single electron. The immediacy is explained because the energy is delivered in one step, not accumulated from many tiny contributions. That binding cost is the work function, a material-dependent energy threshold. The electron must pay it to leave the metal, and only the leftover becomes kinetic energy that can be measured. Different metals have different work functions, which shifts the threshold frequency. The surface is not a featureless plane, but a structured environment, where electrons are held by electromagnetic forces and the collective behavior of the solid. So the maximum electron kinetic energy is hnu minus the work function. Increase intensity, and you increase the count of emitted electrons, not their maximum energy, because each electron still receives only one quantum in the simplest picture. The slope of energy versus frequency becomes a direct measurement of h. That is one reason the photoelectric effect became so important, because it turns a mysterious constant into a measurable quantity. Below the threshold frequency, hnu is too small to pay the work function. No amount of additional quanta helps any single electron because each quantum is still too weak, and electrons do not combine many weak quanta into one escape in the observed way. The gate remains closed. The failure is not due to insufficient total energy in the beam, but due to insufficient energy per interaction. This is the photoelectric shock, because it makes frequency primary and intensity secondary. It makes colour a measure of per quantum energy, not merely a wave label tied to wavelength. The spectrum becomes a set of energy denominations. Once you accept that, the threshold frequency is not mysterious, because it is simply the point where a single denomination becomes large enough to pay the fee. It also makes the photon feel inevitable, even if the name comes later. A quantum of light is not a metaphor here. It is the simplest accounting that matches the data with minimal strain. The phenomenon reads like a ledger that only accepts certain coin values. The metal does not negotiate with partial payments, and the experiment keeps proving that stubbornly. Yet it is unsettling, because it does not erase the wave evidence. Interference and diffraction still demand a wave description in space, and those patterns can be mapped with exquisite detail. Light refuses to choose a single classical identity. The same beam that ejects electrons in discrete events can also paint smooth fringes across a screen, and both behaviors are real, so the story becomes a rupture rather than a replacement. Light propagates like a wave, yet interacts as if it comes in discrete countable units, depending on what we ask it to do. The same entity seems to obey two incompatible instincts. The rupture is not a failure of observation, but a clue that our categories, wave and particle, are too blunt for what nature is doing. We can say the key rule plainly, because it will return again and again. Photon energy is proportional to frequency, and Planck's constant sets the scale, linking a measurable colour to a measurable energy. It is one of the simplest equations in physics, and one of the most disruptive. A single proportionality ties optics to thermodynamics, and it quietly rewrites what brightness can mean at the microscopic level. This connects directly to colour in the visible range. Red photons carry less energy than blue photons, and ultraviolet photons carry more than either, even though the difference is invisible to our eyes beyond violet. The rainbow becomes an energy gradient. If we could see energy directly, the spectrum would look like a staircase of increasing per photon cost, not just a palette of hues. The proportionality also explains why ultraviolet light can trigger chemical changes and biological damage more readily. Each quantum can cross energy barriers that red light cannot, breaking molecular bonds or altering electronic states. The danger is not the brightness alone, but the per photon punch. A dim ultraviolet source can be chemically aggressive, while a bright red source can be comparatively gentle because the quanta are smaller. At this point, the central question becomes less abstract and more urgent. What is a photon really, if it is defined by how energy is transferred, one discrete event at a time? Are we describing a particle, a field excitation, or a rule about measurement? The discomfort is productive, because it forces physics to clarify what it means to say something exists between emission and detection. Einstein's light quantum also implied something else that classical intuition resisted. If light carries energy in packets, it should also carry momentum in packets, because energy and momentum are linked in relativistic physics. A beam should not only heat, but push. The push should be measurable, not as a metaphor, but as a force that can twist a fibre or nudge a mirror. Momentum in classical electromagnetism already existed as a field property. Maxwell's theory predicts radiation pressure, a force exerted by light on matter, because the electromagnetic field carries momentum density and transports it. Even a perfectly absorbing surface must feel a shove. The field's momentum flow can be described by the pointing vector, which points in the direction energy and momentum travel. Radiation pressure was not just a theoretical flourish. Delicate experiments showed that light can push on surfaces, even in vacuum, with a force proportional to intensity, tiny but measurable with sensitive balances and torsion fibers. The push is real, though it is gentle. In a quiet lab, a mirror can be suspended so lightly that the faint pressure of light becomes a detectable twist, like an invisible hand. In a wave picture, the pressure comes from the momentum flow in the electromagnetic field. In a quantum picture, it comes from many small impulses delivered by quanta, each impulse too small to feel alone but undeniable in aggregate. The continuous pressure becomes a rapid sequence of microscopic taps. The two pictures agree on the average force, but they suggest different stories about what happens in each individual exchange. Einstein's reasoning and later developments tie energy and momentum together for light. For a photon, momentum P equals E divided by C, so P equals hnu over C, and the direction of travel sets the direction of the push. The photon carries a vector quantity, not just a scalar energy. That vector character matters because it predicts recoil directions and scattering angles, not merely heating. This relation makes light's push feel less mysterious. A higher frequency photon carries more momentum, and a more intense beam carries more total momentum per second, because more photons arrive each second. The same equation that explains photoelectric thresholds also explains pressure. It is one of the quiet unifications of early quantum theory, because it ties colour, energy, and mechanical force into one consistent package. The cosmos offers gentle reminders that light pressure is real. Comet tails point away from the sun, shaped by radiation pressure and the solar wind, and their delicate streams trace invisible forces across millions of kilometers. Sunlight is not just illumination, it is a wind of momentum. In wide shots, the tail's pale arc is like a diagram drawn in dust, revealing forces we cannot see directly. The effect is small per photon, but enormous in aggregate. Over time, countless photons can nudge dust grains and thin gases into visible structures, sculpting tails, halos, and faint veils of scattered light. The universe is patient, and small forces accumulate. A single photon is negligible, but a star emits an ocean of them every second, and that ocean has weight in motion. The same idea underlies solar sails, which trade patience for fuel. A reflective sheet gains momentum by reflecting photons, each reflection reversing momentum and doubling impulse, so the sail slowly accelerates without expelling propellant. It is propulsion by pure exchange. Visually, a thin sail unfurling against black space makes the concept intuitive. No engine flame, only the steady pressure of sunlight. These examples keep the narrative grounded. Light is not only a mathematical field, it is a physical carrier of energy and momentum across emptiness, connecting stars to dust and instruments to distant sources. The vacuum is not empty of influence. What looks like emptiness becomes a medium for transfer, because the electromagnetic field can cross it and still do work. Still, one could argue that momentum is a field property, not proof of particles. A continuous wave can carry momentum, so radiation pressure alone does not force a granular picture. The deeper test would be a collision, where light exchanges momentum like a projectile with a measurable recoil. A collision is a stricter demand than a steady push, because it asks for discrete bookkeeping of energy and momentum in a single event. That test arrived in 1923 with Arthur Compton's work on X-rays. He scattered high-frequency light from electrons and measured the outgoing wavelength with careful spectroscopy. X-rays were ideal because their photon energies are large, and the shifts become measurable. In the lab, the setup looks almost austere. An X-ray source, a target, and a detector that can resolve subtle changes in wavelength. If X-rays were purely waves, scattering from electrons should preserve frequency in a simple elastic picture, aside from small Doppler effects tied to electron motion. The data showed a systematic shift that could not be dismissed as experimental noise. The scattered light came out redder in a precise way. The shift was not random, and it did not depend on the target material in the way a purely classical wave theory might suggest. Compton found that the scattered X-rays had a longer wavelength, meaning lower frequency and lower energy. The shift depended on the scattering angle, in a precise way, with larger shifts at larger angles. The pattern looked like kinematics, not like a vague loss. It resembled the geometry of a collision, where angles and energies are linked by conservation laws. The simplest explanation treated the interaction as a collision between a photon and an electron. Energy and momentum conservation then predict the observed wavelength change, including its exact angle dependence. The wave becomes a particle-like participant in a two-body event. The collision picture is not decorative, because it yields a specific formula that can be tested point by point. In that collision picture, the photon gives some of its energy and momentum to the electron. The electron recoils, and the photon leaves with reduced frequency, as if it had bounced and paid a toll. The scattered photon still travels at c, but with a changed wavelength. The recoil electron is not a side detail, because its momentum is the balancing entry in the ledger. The formula for the wavelength shift includes Planck's constant and the electron mass. It is not a curve fit, it is a conservation law written in quantum terms, and it matches the data with striking accuracy. The shift becomes a fingerprint of photon momentum. In effect, the experiment reads out h again, but now through scattering geometry rather than emission thresholds. Compton scattering strengthened the case that photons carry momentum as discrete quanta. It made the photon more than a bookkeeping device for emission and absorption, because it behaved like an entity that can exchange momentum in a single event. The recoil electron is the witness. The evidence is compelling because it is differential and angular, not merely an average over many interactions. It also clarified that the photon is not merely a label for energy. It participates in interactions with kinematics, with angles and recoils that resemble particle events, and those events can be counted one by one. The scattering is a geometry of exchange. The photon's particle-like behavior shows up when the experiment demands localized transfer, like a collision that must conserve energy and momentum in a single transaction. And yet the documentary must resist a misleading picture. A photon is not a tiny billiard ball flying through space with a hidden little surface, because that image smuggles in classical properties that do not belong. The photon does not have a rigid boundary or a definite trajectory in the classical sense. When we try to imagine it as a miniature object, we import intuitions that will later fail, especially in interference experiments. The photon is a quantum of interaction, a discrete exchange allowed by the electromagnetic field's coupling to charged matter. It is a unit of what can be emitted or absorbed, and it shows up when energy and momentum change in localized events. The discreteness belongs to the exchange. That framing keeps the wave picture alive, because the field can still be spread out, even when the outcomes are counted. That phrasing matters because it keeps the wave evidence in view. The electromagnetic field can be spread out, but exchanges with matter occur in quantized events, like clicks on a detector or ejected electrons from a surface. The field's influence can be delocalized until the moment it is not. The click is local, but the probability of the click can be distributed across space, and that distinction will become crucial. So the photon is not a miniature object added on top of the field. It is the field behaving quantum mechanically, where excitations come in countable units, and where measurement reveals discrete outcomes. The particle is the quantum of the field. In that sense, the photon is both less and more than a particle. Less because it lacks classical solidity, and more because it is a fundamental mode of the field itself. This is why the word photon can mislead if it is heard as a classical particle. The photon is defined by quantized energy and momentum transfer, not by a rigid shape, and not by a tiny pellet of light. The language is convenient, but it must be handled carefully. Our nouns are old, and quantum behavior forces them to stretch beyond their usual meanings. In experiments, we detect photons as clicks, tracks, or triggered electrons. Those are localized events, but the underlying field description can be delocalized until interaction, and the statistics of many events rebuild the smooth patterns of optics. The world offers points, while the theory offers amplitudes. A screen can accumulate single impacts that look random at first, and then slowly reveal a structured pattern that no classical particle stream should produce. Planck's constant now appears as a boundary marker in the story. It is the scale that separates the smoothness of classical waves from the graininess of quantum exchange, and it tells us when discreteness matters. It is small enough to hide in ordinary life, yet large enough to rule the microscopic world. The constant is not just a number, because it sets the size of the smallest meaningful action in quantum mechanics, a concept that will echo beyond light. When energies are large compared to hnu, the granularity can be ignored, and waves look continuous. When energies are comparable, the granularity becomes unavoidable, and classical averaging fails in exactly the way the blackbody problem revealed. The catastrophe was a warning sign of scale. Classical physics did not fail everywhere, but it failed precisely where its assumption of continuous sharing was pushed into a regime with too many high-frequency modes. This chapter's rupture is therefore not a sudden whim of theory. It is a forced response to experiments that count energy transfer, one event at a time, and that refuse to be smoothed away. Nature is not obligated to honour our preference for continuity. The discomfort is the price of accuracy, and the reward is a set of rules that predict what happens with astonishing reliability. We can summarise the chain in a few dense steps. Classical equipetition fails, Planck quantizes exchange, Einstein quantizes light, and experiments reward the audacity with clean, testable laws. Each step is a response to a curve, a threshold, or a shift that would not go away. The pattern is instructive, because it shows theory bending under the weight of measurement, not drifting into speculation. But the reward comes with a new tension that does not dissolve. If light is made of quanta, why does it still spread, diffract, and interfere like a wave, painting fringes on screens as if it were continuous? The same light that arrives in clicks also draws smooth patterns. The tension is not a minor technicality, because interference is the signature behaviour that made the wave theory so convincing in the first place. The question is not rhetorical, it is the next cliff edge. A photon seems to be both a discrete event and a distributed possibility, depending on what we ask, and that duality is not a mere metaphor. It is an operational fact about how experiments behave. If we dim a light source until detections come one by one, the interference pattern can still emerge, as if each quantum contributes to a wave-like structure over time. So we end this chapter with the central question sharpened rather than settled. What is a photon, really, if it is not a tiny ball, yet it hits with a quantized punch, and if it is not a classical wave, yet it spreads with wave-like grace? The mystery is now focused, not solved. The photon is both a unit of exchange and a bearer of wave-like propagation, and our task is to understand how those statements can coexist without contradiction. In the next chapter, we follow that tension into interference itself. We ask how single photons can build fringes, and what it means to say a quantum travels as a wave, even when it is detected as a point. The wave will return, but it will return changed. The old wave will reappear with a new mathematical role, less like a physical ripple in a medium, and more like a guide to probabilities. We keep the opening hook nearby because it gains weight here. A photon can cross the observable universe, yet it arrives as one discrete exchange, and that duality is the strange heart of light, an old wave that learned to count. We return to the central question with a quieter, sharper tool, an experiment so spare it feels almost like a drawing. What is a photon, really, when the same light behaves like spread and like impact, and when our language keeps slipping between wave and particle? The double-slit experiment is not a trick, and it is not a metaphor, even though it has become a symbol. It is a simple geometry that forces light to answer in patterns, and those patterns are hard to explain away. It is also remarkably forgiving, because the essentials survive across many designs, from tabletop optics to electron beams. Imagine the lab as a darkened room, with a source at one end and a screen at the other. Between them sits a barrier, matte and thin, like a sheet of black metal with a careful cut. The air is still, the mounts are bolted down, and the only bright thing is the faint glow where light finally lands. Start with a screen and a source, and place a barrier between them. Cut one narrow slit, and light makes one bright band centered where straight-line rays would have landed. Even before we talk about quantum ideas, the pattern already refuses to be a perfect geometric shadow. That single band is not perfectly sharp, because edges matter at the scale of wavelengths. Diffraction spreads the band, because wave-like propagation leaks around boundaries, and the slit acts like a new source that fans outward. In classical terms, each point across the opening contributes a little wavelet, and the far screen collects their sum. If we could freeze the light in time, we would see a crest and trough structure sliding forward. In practice, we see only intensity, the time-averaged brightness, and intensity hides the oscillation while preserving its geometry. The electric field can oscillate hundreds of trillions of times per second, far too fast for any direct visual tracking. The width of that band depends on the slit width and the light's wavelength, and the relationship is quantitative. Narrow the slit and the pattern broadens, because constraining position forces a wider spread of transverse momentum. The central maximum grows wider in a way that can be derived from simple trigonometry and a Fourier transform. This is already a hint that ray optics is a special case, not the full story. Rays work when apertures are large compared with the wavelength, but the moment you tighten the geometry, wave behavior announces itself. In the limit of very wide openings, the fringes compress until they are effectively invisible, and our everyday intuition returns. Now cut 2 slits, identical and close together, and keep everything else unchanged. The screen no longer shows 2 simple bands, as if 2 flashlights were shining side by side. Instead, the light seems to organize itself into an alternating architecture of bright and dark. Instead, it shows many bright and dark fringes across the region where light lands. The darkness is structured, not a failure of illumination, and the bright stripes have a steady spacing that can be measured with a ruler. You can predict that spacing from the slit separation, the wavelength, and the distance to the screen. The pattern looks like a barcode painted in light, with bright ridges and deep troughs. If the slits are moved closer, the fringes spread farther apart, and if the screen is moved back, the whole pattern expands. Even the contrast is diagnostic, because it tells you how coherent the source is across the 2 openings. This is what waves do when they have 2 paths. They superpose, and their phases add or cancel at different points on the screen, depending on the path length difference from each slit. A difference of 1 wavelength brings the oscillations back into step, while half a wavelength flips them into opposition. Where peaks align with peaks, the intensity grows, and a bright fringe appears. Where peaks align with troughs, the intensity vanishes, and the screen goes dark in a place that still receives light from each slit. That vanishing is not approximate. It can be almost complete when the setup is clean. The key is that the dark regions are not shadows cast by the barrier. They are cancellations created by the wave's phase, and phase is a kind of timing, an alignment of oscillations, not a change in average energy. 2 contributions can each be non-zero, yet their sum can be nearly zero at a given point. Historically, this behavior helped settle an older argument about the nature of light. Thomas Young's early 19th century interference experiments made the wave picture hard to deny, especially against the particle model favoured by Newton. Young's results joined forces with Fresnel's later work, which turned interference into a precise predictive framework. But the story did not end with waves winning a clean victory. The 20th century reopened the case, because light began to behave like something granular, as if it arrived in indivisible packets. Planck's quantum hypothesis, proposed to explain blackbody spectra, made discreteness feel less like a nuisance and more like a clue. If light were only particles, the prediction is different. Each particle would go through one slit or the other, and the screen would record a sum of independent impacts. The geometry would still matter, but it would matter only as a pair of openings that accept or block trajectories. 2 slits would then produce 2 overlapping bands, like 2 paint sprays adding together. There would be no systematic dark stripes because nothing in a simple particle model subtracts probability. Without a wave-like phase, there is no mechanism for regular cancellation across space. With bright classical beams, the interference pattern is stable and immediate, almost serene in its certainty. It looks like a wave phenomenon because it is, and the mathematics of classical electromagnetism predicts it cleanly. Maxwell's equations, paired with boundary conditions at the slits, deliver the fringe spacing with almost embarrassing confidence. But Chapter 3 left us with a fracture in that calm picture. Light arrives in discrete clicks, and energy transfer is quantized, as if the field pays out its budget in whole units. The detector does not report half a photon any more than a coin toss reports half a head. The photoelectric effect, blackbody radiation, and the counting statistics of detectors all point the same way. Whatever light is, it can behave as if it is made of quanta, and those quanta do not split into arbitrary fractions. Even when a beam is attenuated until it is extremely weak, the energy arrives in complete countable events. So we rebuild the experiment in the single photon regime. We dim the source until detections come one at a time, and we wait long enough to let the statistics speak. The lab becomes a place of patience, because the pattern is no longer drawn in a moment. Technically, this can be done with attenuated lasers, heralded single photon sources, or carefully filtered spontaneous emission. In each case, the goal is the same: make the probability of two photons overlapping in time negligibly small. Engineers verify this with correlation measurements because a true single photon source suppresses simultaneous detections. The screen is replaced by a photon counting detector or by a camera that can register single events. Each event is localized because the detector's atoms absorb energy in a discrete transition. The spot is not a tiny photon splat. It is a macroscopic record produced by microscopic absorption. A modern sensor might be an avalanche photodiode, where one absorbed photon triggers a cascade of charge carriers. Or it might be an intensified camera, where a single photon becomes a visible flash on a phosphor screen. In both cases, amplification is the point, because the quantum event must be lifted into the classical world of stable records. At first, the detections look random, like scattered dust on black velvet. Each click is a point, not a stripe, and not a continuous smear, and the room feels almost too quiet for something so famous. The apparatus is doing its job, but it offers no immediate reassurance that it understands the story we expect. You can watch the pattern being built like a slow snowfall. One dot appears, then another, and for a while there is no hint of order, only the sense that chance is drawing a map. The early frames look like noise, the kind you might blame on the electronics. Then the points accumulate, and the pattern emerges slowly. The same bright and dark fringes appear, as if a wave were present, even though the experiment is engineered to send photons one at a time. The orderly stripes arrive not as lines, but as a statistical sculpture assembled from clicks. This is the quiet madness at the heart of quantum duality. Each photon arrives as a particle-like event, yet the statistics are wave-like, and the wave-like part seems to know about both slits. The experiment does not merely suggest a paradox, it operationally enforces it. We are tempted to say each photon interferes with itself, and that phrase has a certain poetic accuracy. Yet it can mislead if taken too literally, as though a tiny object splits and recombines like a droplet. The better statement is colder, and therefore more reliable. What we actually have is a rule for predicting outcomes, and the rule is not optional. Quantum mechanics assigns an amplitude to each possible path, and the amplitudes combine before we talk about probabilities. The order matters, first add then square, because nature seems to care about phase. An amplitude is not a physical ripple like water in a canal. It is a mathematical quantity that can be added and can cancel, and it can carry a phase that behaves like an angle. That phase is invisible to a single click, yet it becomes visible in the pattern of many clicks. In the double slit, there are two main alternatives. The photon could be detected after passing slit A or after passing slit B, and the apparatus is designed so those alternatives cannot be told apart. The slits are aligned, the timing is matched, and nothing downstream marks the route. Quantum mechanics tells us to add the amplitudes for alternatives that remain indistinguishable. The sum is the amplitude for detection at a specific point on the screen, and the sum can be larger or smaller than either part. In some regions, the two contributions reinforce, and in others they nearly erase. Then we convert amplitude into probability. This step is the born rule, and it is the bridge from possibility to frequency, from a complex number to a count rate. It is also one of the theory's most mysterious ingredients, because it connects smooth evolution to discrete events. The probability is proportional to the squared magnitude of the total amplitude. In symbols, probability goes like amplitude squared, which is why cancellations can drive probability nearly to zero. Squaring also explains why negative or complex amplitudes can still yield positive probabilities. A gentle way to hold this is to imagine ripples of possibility spreading from each slit. The ripples are not matter, yet their overlap shapes outcomes, and their relative phase determines whether they reinforce or erase. The screen does not reveal the ripples directly, it reveals their squared result. In a vivid visualization, each slit becomes a source of faint expanding rings. Where the rings line up, brightness grows, and where they misalign, the screen stays dark, even though each ring alone would have contributed. The darkness is therefore an active feature of the mathematics, not a passive absence. When two amplitudes align, the squared magnitude grows, and detections become more likely there. When they oppose, probability drains away, and the detector almost never clicks in that region. The word almost matters, because real experiments have finite coherence and imperfect alignment. So the dark fringes are not places where photons travel and then disappear. They are places where the probability of arrival is near zero, because the alternatives cancel before probability is assigned. The cancellation happens in the amplitude bookkeeping, and the bookkeeping predicts the counts. This is why single photons can build an interference pattern. Each click is random, but the randomness is not arbitrary, and it is not a sign that physics has stopped making predictions. The predictions have moved from certainties about paths to certainties about distributions. It is guided by a probability distribution that contains phase information. The phase is what allows cancellation, and cancellation is what makes fringes, and the fringes are what force us to rethink path. We are not watching tiny bullets miss their targets. We are watching a rule about alternatives shape the statistics. We can now say something precise about wave and particle language without trying to force a single picture. The photon is not a classical wave, and it is not a classical particle, even though it can resemble either one. The experiment punishes any attempt to keep only one metaphor. The wave-like part is the amplitude structure that evolves and superposes. The particle-like part is the discrete outcome when an interaction occurs, because detectors record energy and localize stable events. In quantum field language, the photon is an excitation of the electromagnetic field, and detection is the field exchanging a quantum with matter. Between emission and detection, the theory does not assign a single definite trajectory. It assigns a superposition of alternatives, and those alternatives are weighted by amplitudes that can interfere. The state evolves smoothly according to a wave equation, even though the outcomes do not look smooth. Superposition is not a claim that the photon is literally split into two halves. It is a claim that the state includes multiple possibilities at once, and that the possibilities must be combined coherently. Coherence is the fragile ingredient, because it can be lost when the environment learns too much. Those possibilities are not mere ignorance about a hidden path. They are the content of the quantum state that predicts interference, and the evidence is the pattern itself. If we could replace the photon with a classical lottery ticket, the cancellations would have no place to come from. If you insist on a classical story, you quickly run into contradictions. The photon cannot be said to really go through one slit while still producing cancellations that require both alternatives to be present in the calculation. The experiment does not allow the comfort of an unseen but definite route. Now we add the most famous twist, the one that turns the experiment into a philosophical pressure test. If we try to learn which slit the photon used, the interference fringes disappear and the screen becomes ordinary again. The pattern does not merely change a little, it changes its entire character. Place a detector at slit A or slit B, or mark the pairs with any physical tag that can be read out later. The pattern changes, and the fine dark stripes wash away into two broad humps. It is as if the experiment stops asking about phase and starts asking about routes. The screen now shows two broad bands like particle addition. The structured dark fringes are washed out, and the result looks like what a naive particle model would have predicted from the start. The surprise is not that particles make bands, but that the bands appear only when we force the question. This is not because a human mind looked at the data, and it is not because awareness has mystical power. It is not consciousness that collapses anything in the laboratory, because the effect happens even if no one checks the record. The universe does not wait for an audience. It is information in the physical sense, and information always has a carrier. Which path information means the environment carries a record correlated with the path, and that record can exist in electronics, scattered photons, or vibrations. Even a tiny recoil of an atom can, in principle, become a label. When the photon becomes entangled with a detector, or with stray degrees of freedom, the alternatives are no longer indistinguishable. The state of the photon is no longer separable from the state of the apparatus. The price of knowing the path is that the phase relation becomes unusable for interference. The amplitudes for the two paths no longer combine coherently at the screen. The phase relationship becomes inaccessible to interference, because the phase is now tied up in correlations with the path marker. What was once a single, coherent sum becomes a mixture of effectively separate histories. In practical terms, the path marking device makes the two histories separable. The quantum state spreads into a larger state of photon plus apparatus, and the which slit label becomes part of the physical description. Once the label exists, even in principle, the interference term loses its grip on the visible pattern. This is where decoherence enters as a quiet, technical word with dramatic consequences. When many environmental degrees of freedom become correlated with the path, the interference terms effectively average out and the pattern loses contrast. Decoherence does not require a conscious observer. It requires only uncontrolled entanglement with the surroundings. The interference is not destroyed by moral judgment. It is destroyed by entanglement, which turns phase into a private correlation, and private correlations cannot create visible fringes on the screen. The phase still exists in the larger state, but it is no longer available to the simple measurement we call the screen. This is why even weak witch path marking can reduce fringe visibility. Partial information yields partial loss of interference, and the pattern fades gradually rather than snapping off like a switch. The experiment becomes a dial rather than a binary, and that dial can be turned with careful optics. You can quantify this with a visibility measure, comparing the brightest and darkest fringes. As distinguishability increases, visibility decreases, and the trade-off is not a matter of taste. It is a constraint that can be written down, tested, and repeatedly confirmed. The deeper point is that quantum mechanics is not about what we know. It is about what correlations exist in the world, and what correlations are possible given a particular experimental arrangement. Knowledge is a human word, but correlation is a physical one. At this point, Niels Bohr's principle of complementarity becomes a calm guide rather than a slogan. You can build an experiment to reveal wave-like behavior, and the fringes will answer. Or you can build an experiment to reveal particle-like path information, and the apparatus will return a definite route. But you cannot fully reveal both in the same setup, because the requirements conflict at the level of physical correlations. To preserve interference, you must preserve indistinguishability, and to learn the path, you must create a distinguishable record. The contradiction is not psychological. It is engineered into the experimental logic. Complementarity is not a ban on curiosity, and it is not a confession of ignorance. It is a statement about mutually exclusive experimental arrangements, where sharpening one kind of question blurs the other. The world does not refuse answers, but it insists that some answers cannot be simultaneously sharp. The apparatus defines which questions have sharp answers. The photon does not carry a full set of classical properties waiting to be read, like labels on a suitcase, because the labels depend on how you choose to look. The measurement context is not a footnote. It is part of the phenomenon. This leads naturally into the uncertainty principle, which is often described as measurement disturbance. Disturbance can happen, but that is not the core, and the deeper idea is more structural. Even with an ideal gentle measurement, the trade-off remains. The core is that certain pairs of quantities are represented by non-commuting operators. The state cannot make both sharp at once, because the mathematics of the theory forbids a joint, perfectly definite assignment. In plain language, the rules do not allow a single state to encode perfect answers to both questions. Position and momentum are the standard pair, and the double slit makes them feel intuitive. Narrow slits localize position at the barrier, because the photon's transverse position is constrained by the opening. The barrier acts like a spatial filter, forcing the wave function into a tighter profile. That localization increases momentum spread, and the outgoing pattern broadens accordingly. Precision in one domain implies spread in the other, and the relationship can be written as a lower bound on the product of uncertainties. The screen becomes a visible histogram of that momentum spread. This is not clumsiness of instruments, though instruments always have limits. It is a feature of the wave-like amplitude structure that underlies probabilities, and it appears even in idealized calculations. The uncertainty relation is therefore not a technological complaint, it is a structural fact about states. We can keep this beginner-friendly by staying with patterns, because patterns are the visible trace of momentum. A narrow aperture produces a wide diffraction pattern, because sharpness in space requires many momenta. The broader the momentum distribution, the wider the range of angles at which clicks appear. In Fourier language, a tight spatial profile contains many spatial frequencies. The uncertainty principle is the quantum version of that wave fact, and it survives even when the detections come as discrete clicks. The mathematics is sophisticated, but the intuition is already on the screen. Quantum mechanics generalizes that wave logic, but it applies even when outcomes are discrete. The click is sharp, yet the distribution is constrained, and the constraints are written into the state. We trade certainty about individual events for certainty about the shape of the statistics. Now we step back and ask what the quantum state really is, because the temptation is to imagine a ghostly substance. It is not a physical wave of stuff filling the room, sloshing like a fluid between source and screen. If it were, we would expect energy to be smeared out, and detectors would behave very differently. It is a compact encoding of probabilities for all possible measurement outcomes. It is a rule for what clicks can occur and how often, given a specific preparation and a specific measurement. In practice, it is the object we update when we change the apparatus, because the apparatus changes the questions. In some interpretations, the state is a real field-like object. In others, it is a catalogue of expectations, and reality is in events and correlations, but the operational predictions remain the same. The documentary does not need to choose a camp to respect the data. For this chapter, we do not need to settle interpretation, and we should resist the urge to pretend we can. We need the operational fact that amplitudes add, and probabilities come from squares. That simple rule, repeated across experiments, is the engine of the quantum strangeness. We also need the idea that measurement is an interaction that produces a definite record. A detector click is a macroscopic stable event, amplified beyond microscopic ambiguity into something that can be stored and compared. The record is what lets science be public, repeatable, and cumulative. The click is where the photon's energy and momentum are exchanged. It is where the field excitation becomes a localized transfer, often by promoting an electron to a higher energy state that triggers a chain reaction. The details vary by detector, but the logic is consistent: microscopic absorption, then amplification. Between clicks, the photon is best described by a quantum state that can be spread out. That spread is not a smear of energy like fog, because the energy is not continuously deposited across space. It is a spread of probability amplitude, and that amplitude can interfere with itself. It is a spread of probability amplitude, which can interfere. The interference is real because it changes observed frequencies of outcomes, and those frequencies are what experiments actually measure. A pattern is not a philosophical preference, it is a data set. If you want a mental image, imagine a map of likelihoods hovering in space, updating smoothly as the state evolves. The map is not the territory, yet it is the best tool we have for predicting where the next dot will appear. And when the map predicts a dark fringe, the detector obeys with near silence. We now introduce a gentle entry into Hilbert space using polarization, because it is a clean, two-option system. Polarization is a simple quantum degree of freedom, and it can be manipulated with familiar optical elements. It's also a place where superposition can be drawn as geometry, not as algebra. A photon can be horizontally polarized, vertically polarized, or in a superposition of the two. The language is familiar from polarizing filters, sunglasses, and the way glare can be reduced by selecting an orientation. In electromagnetic terms, polarization describes the direction of the electric field's oscillation, but quantum mechanics turns that direction into a state label. In quantum terms, those polarization options form a two-dimensional state space. The photon's state is a vector in that space, and the vector's direction encodes the probabilities for different measurement settings. Rotating the measurement basis is like rotating the axes on a graph, and the probabilities shift accordingly. A linear polarizer is a measurement device for polarization. It projects the state onto an axis and yields a definite outcome, either transmission or absorption, and the outcome is again a discrete event. The polarizer does not reveal a pre-existing answer, it enforces a question and returns a result. If the photon is prepared at 45 degrees, then measuring in the horizontal-vertical basis gives random outcomes with predictable probabilities. Over many trials, the ratio approaches a stable value, even though each individual result surprises you. The stability of the ratio is the calm heart of the theory, even when the single events feel capricious. The probabilities again follow the Born rule. The squared overlap between the state vector and the measurement axis sets the outcome rates, and the geometry of angles becomes the arithmetic of chance. A simple cosine becomes a prediction about counts, and the lab confirms it with stubborn consistency. This is a clean place to feel superposition without heavy math, because the state is not a hidden coin flip. The photon is not secretly horizontal or vertical before measurement, even if we wish it were. If it were, the statistics under rotated measurements would not match what we actually observe. The state encodes both possibilities, and the measurement context selects which question is being asked. The answer is a discrete click in one channel, and the statistics across many clicks reveal the underlying structure. This is the same logic as the double slit. expressed in a simpler internal degree of freedom. We can also mention circular polarization as another basis choice, because it shows how phase enters quietly. Left and right circular states are superpositions of horizontal and vertical, with a specific phase offset. The phase difference is not decoration. It determines whether the electric field rotates clockwise or counterclockwise as time passes. Phase returns here as a quiet theme, connecting polarization to interference. It is not visible in a single outcome, but it shapes interference and basis changes, and it determines how superpositions transform under optical elements. The same invisible phase that paints fringes on a screen also rotates a polarization state in Hilbert space. A quarter-wave plate, for example, can convert linear polarization into circular by delaying one component relative to the other. In the mathematics, that delay is a phase shift, and in the lab it is a thickness of crystal. A piece of carefully cut birefringent material becomes, in effect, a dial for quantum phase. Polarization also connects back to Witch path marking, and it does so in a way we can almost see. If Slit A tags the photon as horizontal and Slit B tags it as vertical, interference vanishes, because the paths are now labelled. The photon carries its own path record inside an internal degree of freedom. The paths become distinguishable in principle, even if no one reads the tag. The polarization record is enough to block coherent addition, because the total state now contains path information in an internal degree of freedom. The screen sees a mixture, not a coherent sum, because the two alternatives no longer overlap in the same polarization state. But if we erase the Witch path information by measuring in a different polarization basis, interference can be recovered in conditional statistics. The fringes return when we sort the data by the outcomes of the erasing measurement. The pattern reappears not as a universal picture, but as a correlation-dependent one. This is the quantum eraser idea in its simplest form, and it is often misunderstood. It does not rewrite the past, and it does not send influence backward in time, because the raw, unsorted data still shows no fringes. What changes is the bookkeeping of correlations, not the history of a single photon. What changes is which correlations are selected in the data, and which subsets are compared. The experiment reminds us that information is not a story we tell ourselves, but a physical relation between systems. When the relation is erased or blurred, interference becomes available again in the appropriate conditional slice. The lesson stays consistent even as the setups become more elaborate. Interference requires indistinguishability of alternatives in the relevant degrees of freedom, and distinguishability can hide in places you did not think to look. A tiny polarization tag, a stray scattered photon, or a thermal vibration can all become an accidental witness. Now we add a brief teaser of entanglement, because it is the next escalation of the same logic. Photons can be created in pairs, and the pair can share a state that cannot be reduced to properties of either photon alone. The weirdness is no longer about one object and two slits, but about two objects and one shared description. In parametric down conversion, a pump photon in a nonlinear crystal produces two lower energy photons. Energy and momentum are conserved, and the crystal structure provides the conditions that make the conversion probable. The process is rare, which is why the lab lights dim and why the detectors wait. Visually, you can picture a bright pump beam entering a transparent crystal, then faint cones of emission emerging. With careful alignment, two photons are produced together, their directions and frequencies linked by conservation laws. When the geometry is tuned, the pair behaves like a single quantum system distributed across space. The pair can be entangled in polarization, meaning neither photon has a definite polarization alone. Only joint measurements show sharp correlations, and the correlations can violate what any classical shared variable story would allow. The violation is not a matter of interpretation, it is a matter of measured statistics. Measure one photon's polarization, and the other statistics change in a correlated way, even when they are far apart. The change is not a signal sent through space, but a reshaping of conditional probabilities. Locally, each observer still sees randomness, yet together they see structure that cannot be faked by classical bookkeeping. This does not allow signaling faster than light, because the local outcomes remain random. The strangeness is in the pattern of correlations, which becomes visible only when the results are compared. The universe keeps causality intact, while still refusing a naive picture of separable properties. Entanglement reframes the word information again, and it does so with precision. The information is not in either photon separately, but in the shared quantum state, and the shared state is what carries the predictive power. It is as if the answer lives in the relationship rather than in the parts. The double slit already hinted at this, because which path information can leak into the environment. Entanglement is that leakage made explicit, and it shows how lost interference is often interference redistributed into larger correlations. The fringes do not vanish into nothing, they vanish into degrees of freedom you're no longer measuring. We do not go further here, because a later chapter will unpack Bell tests and non-classical correlations carefully. For now, we plant the seed, and we let the seed sit beside the double slit as a related mystery. The same quiet logic, add amplitudes, then square, will return with higher stakes. So where does this leave the photon, in the middle of our documentary arc with the screen still glowing in stripes? It is a quantized excitation that produces discrete events, and it cannot be divided into smaller detection units. Yet it is governed by a state that evolves like a wave of probability amplitudes. The wave and particle words point to different aspects, and neither word alone is faithful to what the experiment demands. The double slit is the cleanest demonstration that our old categories are incomplete. The photon is neither a tiny pellet nor a water-like ripple, and the pattern refuses to be narrated as a single classical history. It is a quantum object whose behavior depends on the question asked by the apparatus. The apparatus is not an observer, it is an interaction, and interactions are what turn amplitudes into records. Once a record exists, the world behaves as if one outcome happened because one outcome did. This is why the experiment feels like quiet madness, even when the mathematics is calm. The world is lawful and consistent, yet it refuses classical storytelling, and it forces us to treat probability as a primary feature. The most unsettling part is not randomness, but the disciplined way randomness is sculpted. What does it mean that the universe can be perfectly predictable in its statistics, while remaining irreducibly unpredictable in each individual event? What does it mean that path is not a property, but a question? And what does it say about explanation, when the best explanation is a rule for outcomes rather than a movie of causes? We can now connect back to the opening hook, without resolving it yet, because resolution would be dishonest. A photon can cross the observable universe, then end as one click, and no classical movie of its journey is provided. The theory gives probabilities, and the world gives events. Quantum mechanics tells us how that click's probability is distributed across space and time. It does not give the photon a classical journey, and it does not promise that such a journey exists between emission and detection. The demand for a single, continuous story may be a demand the universe never agreed to satisfy. And now, we prepare the next transition, because another rule waits behind the quantum one. Relativity will tell us something even stranger, and it will do so with the same kind of uncompromising clarity. The photon is not only quantum, it is also a messenger constrained by spacetime geometry. A photon does not have a rest frame, and along its path the proper time is zero. The messenger that obeys quantum probability also slips past time, and the combination will sharpen the mystery rather than soften it. How can something that leaves no proper time trace still participate in interference, delay, and detection? In the next chapter, we let the quantum description stand, and we ask what space-time says about the same traveller. The photon will become stranger by becoming more precise. A photon can cross the observable universe and still arrive as one detector click, a single count in a photomultiplier or a pixel turning bright. In the lab, that click may be a brief avalanche of electrons, yet it still registers as one indivisible event. The phrase that no time passes in its own frame sounds like a paradox, because our intuition insists every traveller must carry a ticking clock. This chapter treats that phrase as a careful limit, not a literal viewpoint, and it asks what the limit actually means. We begin with special relativity as geometry, not as machinery that slows clocks. In the early 20th century, Einstein reframed a puzzle that Maxwell's electromagnetism had already exposed. Light seemed to demand one universal speed. Maxwell's equations predict electromagnetic waves that propagate at a speed fixed by electric and magnetic constants, not by the motion of the source. That prediction clashed with older ideas, where velocities add like ordinary numbers and where a wave usually needs a medium. In the 19th century, physicists proposed an ether to carry light, then tried to detect Earth's motion through it. The Michelson-Morley experiment became the famous turning point, because it found no ether wind within its sensitivity. Lorentz and Poincaré developed mathematical fixes, and Einstein made the radical move of treating the invariants as fundamental. The solution was not to modify light, but to modify the stage on which motion is measured. Spacetime combines space and time into one structure with an invariant interval. In everyday terms, the interval is a distance measure that mixes meters and seconds using c as the conversion factor. It is built so that all inertial observers, despite disagreeing about time and distance separately, agree on one combined quantity. Different observers slice that structure differently, assigning different times and distances to the same pair of events, yet the interval stays the same. Imagine a clean visual, a Minkowski diagram with time rising upward and space stretching sideways like a calm horizon. World lines cut through that grid as bright threads, and the 45-degree lines mark the speed of light. The diagram is spare, almost architectural, and it rewards careful looking. In that picture, relativity is not a set of tricks. It is a rule about how those threads can tilt. Events that can influence each other must lie inside each other's light cones, the regions bounded by those 45-degree lines. Outside the cone, separations are space-like, and no signal travelling at or below c can connect them. Inside the cone, separations are time-like, and a slower-than-light traveller can move from one event to the other. The light cone is not decoration, it is the causal skeleton of the theory. The speed of light is invariant because spacetime has a fixed conversion between time and space. If c changed with the source, causality would fracture across frames, because different observers could disagree on which events can influence which. Maxwell's equations already hint at a universal wave speed, and relativity makes it a rule that holds for all inertial observers. The rule is severe, because it constrains not only light but every possible influence. This invariance is not a philosophical preference, it is encoded in the Lorentz transformation. When one observer moves relative to another, their coordinates mix. Time picks up a piece of space, and space picks up a piece of time. The mixing is tuned precisely so that light still traces the same 45-degree boundary in every inertial frame. In algebra, this is the demand that the spacetime interval remain unchanged under the transformation. In this geometry, time dilation and length contraction are not forces acting on objects. They are the cost of keeping the interval consistent across moving frames. The bookkeeping required when different observers draw different grids on the same spacetime. A moving clock traces a different path through spacetime, so its proper time accumulates differently. The effect is not a mechanical slowing inside the clock, even though every physical clock will reflect it. Proper time is the time a clock actually measures along its world line, and it is the invariant that replaces absolute time. A wristwatch, a cesium atomic clock, or the oscillation of a stable particle can all serve as approximations to this ideal. In particle physics, lifetimes measured in the lab stretch when particles move fast, and the numbers match the geometry. The key point is simple in plain language. Proper time is what the traveller carries. A massive object can choose a rest frame because it can move slower than c. You can boost into a frame where its spatial momentum vanishes, and in that frame the object sits still while time advances. That possibility defines rest mass as an invariant property, the same for every observer. It is also why being at rest is not absolute. Yet, having a rest frame is meaningful for massive things. Historically, this was part of the shock of relativity. Mass and energy, once separate categories, became different faces of one quantity. The relation E equals mc squared is not merely a slogan, it is a statement about how energy appears in the time component of a 4-vector. Rest energy is what remains when momentum is transformed away. In nuclear reactions, tiny mass differences become enormous energy releases, and the bookkeeping is relativistic to the core. A photon is different because its rest mass is 0. With m equals 0, the energy, momentum relation becomes E equals pc, and the 4 momentum is always light-like. The photon cannot slow below c in vacuum, because there is no rest energy to trade into, and no frame where its momentum disappears. In spacetime terms, its momentum points along the light cone, never inside it. This is not a statement about engines failing to break light, as if photons were tiny bullets with stubborn inertia. It is a statement about the structure of Lorentz transformations and the geometry of Minkowski space. Any attempt to boost into a photon rest frame requires an infinite gamma factor, which is not a physical frame. The mathematics is clear about the boundary, and nature seems to respect it with absolute discipline. Gamma, the familiar factor 1 over the square root of 1 minus v, squared over c squared, grows without bound as v approaches c. For massive objects, gamma can be large but finite, and energy rises steeply as speed increases. Particle accelerators live in this regime, where adding a little speed costs a great deal of energy. For a photon, the limit is already reached. There is no remaining room to boost into stillness. So the popular idea of riding alongside a photon is not allowed by relativity. There is no valid inertial coordinate system where a photon is at rest, and no transformation that turns its light-like form momentum into a purely time-like one. The phrase, in its own frame, is therefore shorthand, and it must be handled with care. If we use it at all, we use it as a signpost toward a limit, not as a literal camera angle. The correct invariant language uses intervals and proper time. Proper time is what an ideal clock measures along its world line, and for time-like paths it is positive and depends on the path through space-time. Two travellers can depart together, reunite later, and legitimately disagree about how much time passed on their own clocks. The twin paradox is not a paradox once the geometry is drawn, because different paths have different lengths in space-time. That disagreement is not an illusion, and it is not about malfunctioning machinery. It is a geometric difference in world lines, visible as different lengths in space-time. In the Minkowski diagram, one path is straighter in time, while another leans into space and therefore accumulates less proper time. The straightness here is not Euclidean, and that subtlety is exactly where intuition tends to stumble. For light, the path is null. The space-time interval along a photon trajectory is 0, and the proper time parameter satisfies dt equals 0. This is why we say a photon follows a light-like world line, a trajectory that sits exactly on the boundary between time-like and space-like separations. It is the razor's edge of causality, where the interval neither behaves like time nor like space. Null does not mean nothing happens in our description. It means that the combination c squared dt squared minus dx squared minus di squared minus dz squared evaluates to 0 along that path. The photon's world line is still a sequence of events in spacetime, but it cannot be parameterized by a ticking proper time clock. If you try to attach a wristwatch to light, the theory refuses because the required rest frame does not exist. The statement T us equals 0 does not mean a photon has experiences. It means the proper time between emission and absorption vanishes in the null limit, which is a geometric fact about the path. It is not a perspective a photon can hold, because there is no rest frame in which such a perspective could be defined. The language is tempting, but the physics is stricter than the metaphor. We can still use coordinates to describe the journey, and those coordinates can span billions of years. In our frame, the photon can leave a galaxy when Earth is young and arrive when civilizations exist, with the beam crossing intergalactic voids that look black and silent. Dust lanes, star fields, and faint hydrogen glow slip past in our imagination, even though the photon never sees them in any literal sense. The long travel time is coordinate time, not proper time. This is where the hook becomes precise. The photon's journey can be ancient in our calendars and still have 0 proper time along its null geodesic. The strangeness comes from mixing everyday time, which is tied to our rest frame, with relativistic invariants, which do not privilege any one observer. Once the distinction is held firmly, the paradox dissolves into a clean statement about geometry. A useful way to keep the logic straight is to imagine a family of massive observers chasing the light. As their speed approaches c, their proper time between two fixed events can be made arbitrarily small, even while our coordinate time remains large. Their clocks still tick, their biology still ages, but the interval they accumulate shrinks as their world lines tilt toward the light cone. The photon is the limiting case where that proper time goes to 0. In a Minkowski diagram, you can almost watch this limiting process happen. The massive world line leans closer and closer to the 45-degree boundary, and the proper time length between two intersections compresses. The diagram turns an abstract statement into a visual squeeze, like a ruler being shortened by a change in geometry. The limit is not a narrative about a traveller's thoughts, it is a statement about what the metric allows. Now we connect that geometry to the photon's quantum identity. The photon carries energy and momentum, even with zero rest mass, and it exchanges those quantities in discrete quanta. Its energy is tied to frequency by E equals hnu, and its momentum is P equals h over lambda. These relations were not guessed for elegance, but extracted from stubborn data. Blackbody spectra, the photoelectric effect, and the quantized exchange of light with matter. Those relations are not decorative formulas. They are the operational bridge between wave and particle language. Frequency tells you how quickly the electromagnetic field oscillates in time, while wavelength tells you how quickly it varies in space. Planck's constant sets the scale at which those oscillations come in indivisible packets. In detectors, the field does not drizzle energy continuously. It arrives in chunks that cannot be subdivided below 1 photon. Frequency is not just color, it is the time component of a 4-vector. Momentum is not just direction, it is the space component of the same object, packaged as 4 momentum. Relativity and quantum theory meet in the photon's 4 momentum, which transforms cleanly between observers. What changes between frames is not the existence of the photon, but the measured energy and direction encoded in that vector. In practice, this is why energy and frequency shift together. If one observer measures a higher frequency, they necessarily measure a higher energy per photon, and the momentum magnitude rises in step. The photon is massless, but it is not weightless in the sense of being dynamically irrelevant. Radiation pressure can push comet tails, and intense light can impart measurable momentum to mirrors, because momentum transfer is real. A change in frequency is therefore a change in energy, and in the time component of momentum. When light is redshifted, it is not merely recolored, it is less energetic, and each quantum delivers less energy to a detector. When it is blue shifted, it carries more energy per quantum, and interactions become more violent. At extreme energies, photons can create particle pairs, revealing how frequency becomes a gateway to new physical processes. Special relativity already gives one route to redshift through Doppler effects. Relative motion between source and observer changes measured frequency, because the observer's time coordinate slices the wave differently. The shift is a direct consequence of how time coordinates transform, not a property of the source alone. Even the angle of arrival matters, because frequency and direction are linked by the same Lorentz transformation. Visually, you can picture wave crests as evenly spaced ripples in spacetime. An observer moving toward the source intersects those ripples more frequently, so the measured period shrinks and the frequency rises. An observer moving away intersects them less frequently, and the frequency falls. The same picture can be drawn as tilted grids, where the observer's now lines cut across the wave pattern at different slopes. But the universe also shifts light without relative motion, through gravity and expansion. Those effects belong to general relativity, where spacetime itself is curved and dynamic, and where straight lines must be defined with care. Light still follows the rules, but the rules now live in geometry. The photon remains massless, yet it becomes an exquisitely sensitive probe of the shape of spacetime. General relativity replaces gravitational force with curved spacetime. Free objects follow geodesics, which are the straightest possible paths in that curved geometry, defined by extremizing the spacetime interval. Massive objects follow time-like geodesics, and photons follow null geodesics. The same mathematical structure that defines straight also defines what clocks measure, which is why gravity and time are inseparable here. A null geodesic is the path that keeps the interval 0 while extremizing the route. It is the closest thing to a straight line available to light, even when space and time are warped by mass and energy. Curvature bends those lines, so light can appear to curve without any push. The bending is a change in geometry, not a change in the local rule that light moves at c. This bending is not because photons have mass that gravity pulls on. It is because energy and momentum respond to geometry, and because spacetime defines what counts as straight. The photon's path is a map of curvature, drawn in real time across the sky. Every deflected ray is like a contour line, tracing an invisible gravitational landscape. Historically, this was one of the first dramatic predictions to be tested. In 1919, Eddington's eclipse expedition measured the deflection of starlight near the Sun, and the result matched Einstein's prediction within the uncertainties. The public story was about starlight bending, but the deeper story was about geometry becoming physical. A set of equations became a claim about the sky, and the sky answered. We can see this in gravitational lensing. a galaxy cluster warps spacetime, and background light is deflected into arcs and multiple images, like pale brushstrokes wrapped around an invisible mass. The lens is not glass, it is geometry acting on null geodesics. The effect can be so strong that it produces Einstein rings, nearly complete circles that look like cosmic halos. In a detailed visual, the cluster sits as a dense knot of galaxies, while faint blue arcs curve around it in a near-perfect ring. Those arcs are the same distant galaxy seen along different paths, each path weaving through a slightly different gravitational landscape. The sky becomes a natural interferometer, splitting light into multiple routes. Time delays between those routes can even be measured, turning lensing into a clock as well as a mirror. Lensing becomes a cosmic measurement tool. The amount of bending reveals the gravitational potential along the line of sight, and careful modelling turns arc shapes into mass maps. Because dark matter contributes to curvature, lensing maps mass that emits no light, outlining halos that would otherwise remain hypothetical. In that sense, photons become messengers not just of luminous objects, but of the unseen scaffolding holding galaxies together. There is also weak lensing, subtler but more widespread. Instead of dramatic arcs, background galaxies are stretched by tiny amounts, their shapes coherently aligned across wide fields. Statistical analysis of those distortions reveals the distribution of matter on the larger scales, turning the universe into a laboratory for invisible structure. The signal is delicate, and it demands careful calibration, but it has become one of cosmology's most powerful surveys of mass. The same curved geometry also shifts frequency through gravitational redshift. Light climbing out of a gravitational well loses frequency and arrives redder, while light falling in gains frequency and arrives bluer. The photon's energy changes as measured by observers whose clocks tick at different rates. The key is that frequency is counted by clocks, and gravity changes how clocks compare. This is a direct consequence of the equivalence principle. In an accelerating frame, light exchanged between different heights changes frequency, because the receiver's velocity differs from the emitter's by the time the light arrives. Gravity reproduces that effect because locally it is indistinguishable from acceleration. The principle is not merely philosophical, it is a practical rule for predicting what light will do near mass. A classic mental image helps. Picture an elevator in deep space accelerating upward, with a lamp on the floor and a detector on the ceiling. By the time the photon reaches the detector has gained speed, so it measures a different frequency. Gravity produces the same shift in a stationary tower. The scenario is simple enough to picture, yet it contains the seed of gravitational time dilation. Gravitational redshift is not the photon tiring out in a physical medium. It is a comparison between clocks at different gravitational potentials, and frequency is fundamentally a clock comparison. The emitter and receiver disagree about time rates, so they disagree about how many wave crests arrive per second. The photon is the courier carrying that disagreement from one height to another. Time dilation and gravity is therefore part of the same story. Clocks deeper in a potential run slower relative to clocks higher up, a fact confirmed with atomic clocks separated by mere centimeters. The effect is tiny on human scales, yet it is relentless, and it accumulates with time. In strong gravity near compact objects, the same principle becomes dramatic, stretching signals and dimming light in ways that shape what we can observe. We can test this with precision, from laboratory towers to satellites. The Pound, Rebka experiment measured gravitational redshift using gamma rays in a Harvard tower, exploiting the Nussbauer effect for exquisite sensitivity. GPS must correct for both special relativistic motion and general relativistic gravitational time dilation, or its position errors would grow rapidly. The remarkable point is that everyday navigation depends on the same geometry that governs photons crossing galaxies. The system works because the geometry is real, not optional. A satellite's clock is higher in Earth's gravitational field, so it runs faster, yet it is also moving quickly, so special relativity slows it down. Engineers do not debate the philosophy, they apply the corrections and the navigation signal arrives where it should. The photon, carrying timing codes, becomes a practical demonstration that spacetime is not just theory. Curved spacetime also affects arrival times, even when frequency is not the focus. Light passing near a massive body takes longer to arrive than a naive straight path would predict, even if source and receiver are fixed. This is the Shapiro delay, a time-of-flight signature of curvature. It is subtle, but it is measurable, and it turns the solar system into a precision timing experiment. Shapiro delay comes from two linked effects. The path is geometrically longer because the null geodesic bends around the mass, and the coordinate description in common charts reflects gravitational potential in the time component. Locally, in a freely falling frame, light still moves at c. The delay is not a slowdown of light in the local sense, but an imprint of how spacetime is stitched together. This delay is measurable in radar echoes and in signals passing near the Sun. When a radio signal grazes the solar limb on its way to a spacecraft and back, the round-trip time increases in a way that matches general relativity. The photon becomes a timing probe of spacetime curvature, as if the universe were adding a subtle pause. The measurement is a reminder that distance and time are not separate bookkeeping columns in curved spacetime. The same idea appears in pulsar timing and in signals near compact objects. When light threads a deep potential well, the travel time can change enough to be detected as a shift in pulse arrival. Timing becomes astronomy's most delicate ruler, and photons are the ticks. In some systems, the delays and redshifts intertwine, and teasing them apart becomes a test of both astrophysics and relativity. Now we widen the stage to cosmology, where spacetime expands. On large scales, galaxies separate because the scale factor grows, and the metric that measures distances changes with cosmic time. Light still follows null geodesics, but those geodesics thread a changing metric, like a line drawn on a stretching fabric. The expansion is not galaxies flying through space like shrapnel, but space itself evolving in the equations. Cosmological redshift is not the same as a simple Doppler shift, though it can resemble one at small distances. The wavelength stretches with the expansion, scaling with the scale factor, so successive wave crests are laid down farther apart as the universe grows. As lambda grows, frequency falls, and photon energy decreases. The effect is universal, because it comes from the background geometry rather than local motion alone. A vivid way to picture this is to imagine a long train of crests travelling through space. The crests do not slow down locally, yet the distance between them increases because the spatial scale itself is changing. The photon arrives with the same identity, one quantum, but with a gentler frequency. In spectral lines from distant galaxies, the pattern is shifted like a familiar melody played in a lower key. This raises a question about conservation. If photons lose energy as the universe expands, where does that energy go, and who receives the accounting entry? The careful answer is that global energy conservation is subtle in an expanding spacetime, and the usual intuition depends on symmetries the universe does not have. When time translation symmetry is absent, the concept of a single conserved total energy for the entire cosmos becomes slippery. In general relativity, energy is conserved locally through the stress. Energy tensors divergence-free condition. Locally, interactions still balance energy and momentum, and every scattering event has a consistent ledger. But a global conserved energy for the whole universe is not guaranteed without time translation symmetry, and expanding space breaks that symmetry. The conservation law survives where it is physically enforceable, in local measurements and local exchanges. So cosmological redshift does not violate local physics. It reflects that the background geometry changes between emission and absorption, so the meaning of energy depends on the local time coordinate used by the observer. The photon's energy is measured relative to local clocks, and those clocks belong to different cosmic times. The same photon can be described consistently, but the numbers attached to it are tied to the observer's slice of spacetime. We can still narrate the journey in familiar terms. A photon emitted when the universe was smaller arrives with a longer wavelength, and the change is smooth rather than abrupt. The stretching is not friction, it is geometry, changing the relation between successive wave crests, a quiet transformation spread across billions of years. The universe does not need to take energy into a reservoir, because the bookkeeping itself is different on a dynamic background. This makes cosmological travel a natural setting for the doesn't age phrase. Coordinate time can be enormous, while proper time along the null path remains zero, and both statements can be true without contradiction. The photon links distant epochs without carrying its own clock, acting as a messenger between times. It is a bridge built from null intervals, connecting when-then to now. The oldest light we see is the cosmic microwave background. These photons last scattered when the universe cooled enough for electrons and protons to form neutral atoms, allowing light to travel freely rather than ricochet through plasma. That moment is recombination, about 380,000 years after the Big Bang. It is also when the universe became transparent, so the CMB is sometimes called the surface of last scattering. Before recombination, the universe was a hot plasma that scattered photons constantly, like a fog so thick that light could not travel far. Photons were trapped in a dense sea of charged particles, exchanging energy and direction in endless collisions. The mean free path was short, and the cosmos was opaque, even though it was filled with radiation. After recombination, the fog cleared, the universe became transparent, and photons streamed freely. Those photons have been travelling ever since through expanding space and evolving structure. Over time, their wavelengths stretched from the infrared and visible range down into microwaves, and their energies fell accordingly. What was once the glow of a hot early cosmos is now a faint, nearly uniform bath. The same radiation that once dominated the universe's energy budget now whispers at the edge of detectability. Today the CMB is cooled to about 2.725 Kelvin. Its spectrum is an almost perfect blackbody, a thermal curve that matches the physics of radiation in equilibrium with astonishing precision. The fit is so clean that deviations are measured in parts per 100,000, and those tiny deviations carry enormous information. Tiny anisotropies, temperature differences of tens of microkelvin, encode early density variations that later grew into galaxies. Visually, the full-sky CMB map looks like mottled colour noise, a delicate stippling spread across the celestial sphere. Those speckles are not detector artifacts. They are the fossil imprint of sound waves in the primordial plasma. Each hot and cold patch marks a region that was slightly denser or slightly rarer when the universe first became transparent. The pattern is a portrait of the universe as a young, vibrating fluid. The CMB also shows how gravity and expansion combine. Photons climb out of evolving potential wells, gaining or losing energy through the integrated Sachs Wolf effect, and the effect depends on how those wells change with time. The pattern becomes a record of geometry changing over cosmic history, not just a snapshot of the early universe. It is a reminder that even ancient light continues to be edited by the universe it traverses. Across the universe, lensing distorts the CMB as well. Large-scale structure deflects the photon paths, remapping anisotropies in a subtle but measurable way, and the result is a blurred, sheared version of the original pattern. Again, the photon is a tracer of null geodesics through a lumpy metric, and the sky becomes a gravitational fingerprint. By measuring that remapping, cosmologists infer how matter clustered over time, including matter that never shines. At this point, we return to the central question with higher stakes. What is a photon, really, if its quantum energy is tied to frequency, and its path is tied to space-time geometry, and its travel time depends on the coordinates we choose? The photon is where quantum discreteness meets relativistic invariance, and neither side can be ignored. It is both a count in a detector and a null trajectory in a metric, and the same object must satisfy both descriptions. The phrase, "photons don't experience time," now has a disciplined meaning. Along a null world line, proper time does not accumulate, so the invariant clock time between emission and absorption is zero in that limit. But there is no photon rest frame, and no internal clock viewpoint to narrate, so the phrase cannot be taken literally. The correct statement is about what the spacetime interval allows, not about what a photon feels. We can say it another way that avoids the trap. Any massive observer can move arbitrarily close to C, and their proper time between two events can be made arbitrarily small, even while their coordinate description remains perfectly ordinary. The photon is the limiting case where that proper time goes to zero, and the limit is mathematical rather than psychological. The closer you push a time-like world line toward the light cone, the more proper time thins out. That limit statement is useful, but it is not a story about consciousness. It is a statement about the geometry of Minkowski space and its curved generalization, and about the classification of world lines into time-like, space-like, and null. It is about invariance, not about what it feels like. When the language becomes too human, it hides the precision that makes the idea true. The photon still participates in delays, deflections, and redshifts in our coordinates. It can arrive late because of Shapiro delay, and it can arrive split into multiple images by lensing, and it can arrive cooler because the universe expanded. Those effects are real measurements in our frames, and they are how we infer the structure of spacetime. The photon is timeless in one invariant sense, yet it is an exquisite clock hand for the universe in another. So the photon is both timeless in proper time and deeply time-sensitive in coordinate time. It is the same object described by different invariants and different coordinate choices, and the descriptions are not rivals but translations. The strangeness is not contradiction. It is the cost of precision, an invitation to be careful with words. When we respect the distinction, the mystery becomes sharper, not smaller. We end by setting the next chapter's pivot. Relativity tells us the geometry of the photon's journey, why its path is null, and why no rest frame exists for light. Quantum field theory must tell us what the photon is as an excitation, and why it comes as a countable event in a detector. The geometry explains the route, but it does not explain the click. The photon's weirdness is now layered. It is a quantum that interferes, a massless carrier that cannot rest, and a null traveller that links distant times without accumulating proper time. The next step is to ask what kind of field can produce such a messenger, and what it means for that field to fill the vacuum. If spacetime is the stage, the field is the substance that can vibrate into particles. Transition to Chapter 6. Spacetime explains how light moves and how it redshifts, and it sets strict limits on what a photon's time can mean. A quantum field filling the cosmos must explain what a photon is between emission and detection, and why the click is so sharply real. We ended with a photon as a null traveller, timed by our clocks but not its own. We watched it cross space without aging, and we felt the oddness of that statement. Now we ask what it is in the modern language that actually predicts the click. Classical physics trained us to treat particles as primary, and fields as helpful descriptions. In that older picture, a field was often a bookkeeping device, an invisible map that told particles how to move. Newton had forces acting at a distance, and Maxwell replaced that with a field that fills space. Even then, the temptation remained to imagine the field as secondary, like a convenient story layered on top of little objects. Quantum field theory flips that order and keeps the flip, even when it hurts intuition. It does not merely add quantization to classical waves, and it does not merely sprinkle probability onto particle trajectories. It rebuilds the ontology from the ground up, and then asks what object means when relativity forbids instantaneous influence. In QFT, fields are fundamental ingredients spread through space and time. They are not just numbers at a point, but dynamical entities with their own equations of motion. Each field comes with constraints from relativity, so influences propagate locally and never outrun light. That locality is not a philosophical preference. It is the mathematical backbone that keeps cause and effect consistent. Particles are quantized excitations of those fields, localized disturbances with discrete exchange rules. The word excitation is literal. The field can be in a ground state, and it can be in a higher energy state that behaves like a particle. In many situations, those excitations travel as if they were tiny objects, which is why particle language remains useful. Yet the deeper description is not a bead moving through emptiness, but a field carrying energy in quantized lumps. This is not a poetic rebranding of waves and pellets. It is a framework that unifies quantum rules with relativity's demand for local, causal interactions. The quantum part forces probabilities and amplitudes, while relativity forces the structure of space-time and the way information can flow. QFD is the compromise that satisfies both, and it is an unusually strict compromise. A field is not an optional medium like the old ether. The ether was imagined as a substance that light rippled through, and experiments like Michelson Morley helped bury that idea. A quantum field is different. It is a set of values assigned everywhere, and it is the thing that can carry energy and momentum. Even if no particles are present, the field still exists as a physical degree of freedom. Visually, imagine a dark, silent grid stretching through space, with every point holding a tiny dial. In classical physics, those dials can swing smoothly, and in quantum physics, they must obey uncertainty. You can still picture ripples moving across the grid, but now the ripples come with discrete accounting. The field is the stage, and the particles are the stage vibrating in countable ways. The electromagnetic field is one of these fundamental fields. Maxwell's equations already told us it can store energy, push on charges, and carry momentum. When it's quantized, its energy comes in discrete units, and those units are photons. The field can still form patterns like waves, but the energy exchange with matter arrives in indivisible packets. So a photon is not a tiny bead riding on a wave. It is one quantum of excitation of the electromagnetic field prepared in a particular state. That state can be sharply localized or spread across kilometers, depending on how it was created. It can be monochromatic like a pure tone, or broadband like a brief flash. The photon is defined by the field's quantum state, not by a miniature trajectory. That state can be spread out and can interfere, as Chapter 4 demanded. The mathematics that predicts fringes is the mathematics of amplitudes evolving and combining, yet the exchanges with matter come in whole quanta, as Chapter 3 forced us to accept. The same formalism produces both behaviors, and it does so without switching theories midstream. Quantization shows up most cleanly in atoms, because atoms are natural frequency filters. Electrons in atoms occupy allowed energy levels, and transitions between levels exchange energy in discrete steps. Those levels are not arbitrary shelves but solutions to a wave equation, constrained by boundary conditions and angular momentum. The atom is a resonant structure, and it only trades energy in the amounts its structure permits. When an atom emits light, it does not drain energy continuously into space. It jumps between levels and deposits one quantum into the electromagnetic field. The timing of the jump is probabilistic, but the energy difference is sharply defined. In a spectrum, that sharpness becomes a line, and in a detector it becomes a discrete event. When an atom absorbs light, it does not sip a little field energy and slowly climb. It takes one quantum that matches the allowed energy difference. If the photon energy is slightly off, absorption becomes unlikely, and the light mostly passes through. This is why transparent materials can sit in bright sunlight without heating instantly, while dark pigments absorb strongly at the right frequencies. This is why spectra look like barcodes. The field can oscillate at many frequencies, but atoms only trade energy at specific gaps. Each element has its own pattern because each nucleus and electron configuration sets different allowed transitions. Historically, those spectral barcodes were clues before quantum theory existed. They were fingerprints that classical physics could describe but not explain. The photon's frequency sets its energy through E equals h nu. Planck introduced H to explain blackbody radiation, and Einstein used the same constant to explain the photoelectric effect. In modern terms, that relation ties the quantum to the field's oscillation rate. Frequency is not just a wave property, it is the label of the photon's energy in a given mode. In this picture, emission and absorption are not tiny projectiles launched and caught. They are discrete changes in the joint state of matter and field. The atom and the field become entangled during the process, even if we later ignore that detail. The photon is the part of the combined state that can propagate outward and be absorbed elsewhere. The click in a detector is the same kind of transition. A pixel, a photomultiplier, or a superconducting sensor records a quantum exchange, then amplifies it. The amplification is crucial because quantum events are small and our world of readouts is large. The detector is a bridge between microscopic discreteness and macroscopic certainty. Now we return to a puzzle that sounded philosophical earlier. Why are photons identical, and why does that sameness matter for interference? The question matters because interference is not a decorative pattern, but a direct signature of how quantum alternatives combine. If photons were distinguishable like coins with scratches, the rules would change. In everyday life, objects have individuality because they carry histories. A baseball has scuffs, a particular path through time, and a unique location that can be tracked. In QFT, field quanta do not come with serial numbers, and the theory never needs them. The field is the entity, and excitations are counted without labels. Two excitations of the same field with the same quantum numbers are not merely similar. They are fundamentally indistinguishable, even in principle. If two photons share the same frequency, polarization, and spatial mode, then swapping them changes nothing observable. The mathematics reflects that by requiring states to be symmetric under exchange. This is not a limitation of our instruments. It is built into the structure of the state space and the way amplitudes are counted. Quantum states for identical particles are not assembled like a list of individuals. They are assembled like occupations of modes, how many quanta sit in each allowed pattern of the field. That change in bookkeeping is subtle, but its consequences are everywhere. Indistinguishability is not a side detail. It is one reason interference works, because alternatives can only interfere when they cannot be told apart. If there is any reliable witch-path information, even in principle, the alternatives stop combining coherently. The pattern on the screen is not just about what happens, but about what could be known. In the double slit, the photon does not need a hidden tag to be itself. The field state evolves, and the detector statistics follow from adding amplitudes. The photon can be prepared so that both paths remain viable descriptions, and then the amplitudes interfere. The result is not a single path plus noise, but a distribution shaped by phase. When alternatives are truly indistinguishable, the amplitudes must be summed before squaring. When alternatives become distinguishable, the interference term disappears. This is not because the photon decides to behave differently, but because the quantum state now includes correlations with the environment. Decoherence spreads phase information into degrees of freedom we do not track, and the fringes wash out. Photons also obey bosonic statistics. Many photons can occupy the same state, which is why lasers can produce coherent beams. In a laser cavity, stimulated emission encourages photons to pile into the same mode, matching frequency, direction, and polarization. The beam's coherence is a macroscopic signature of bosonic piling up. That bosonic sameness is not just about brightness, it shapes how light behaves in cavities, in thermal radiation, and in the quantum noise of measurements. It explains why blackbody radiation follows Planck's distribution, where mode occupation grows with temperature. It also sets the baseline fluctuations in optical experiments, where shot noise appears because photons arrive as discrete counts. Now we take one more step toward the deep structure of electromagnetism. The photon is not only a quantum of a field, it is tied to a symmetry. Symmetry here does not mean a pretty shape. It means a redundancy in our description that leaves observable physics unchanged. Electromagnetism has a gauge symmetry called U1. The gentle idea is that certain changes in the field's phase are physically unobservable. You can rotate a complex phase at every point in space and time, and the measurable electric and magnetic fields remain the same. The theory is built so that only gauge invariant combinations can show up in experiments. Because of that redundancy, we can describe the same electromagnetic situation in many equivalent ways. The physics stays fixed while the bookkeeping shifts. Potentials can change while fields remain unchanged, and different gauges can make different calculations easier. The redundancy is not a defect. It is a sign that the theory contains more description than reality requires. Gauge symmetry is not a trick to hide ignorance. It is a constraint that forces the interactions to take a particular form. When we demand local gauge invariance, we are compelled to introduce a connection field that couples to charge. In plain language, the symmetry requirement essentially generates the electromagnetic interaction. What looks like a mathematical preference becomes a physical law. In QFT language, the photon is the gauge boson of this U1 symmetry. It is the quantum messenger associated with electromagnetic interactions. The coupling strength is set by the electric charge, and the theory's predictions can be tested to astonishing precision. Quantum electrodynamics became a triumph, partly because it made numbers that matched experiments to many decimal places. Calling it a boson does not mean it is a little ball. It means it is an excitation that mediates a force and follows bosonic counting rules. The photon also carries spin 1, which shows up as polarization, yet because it is massless, only two polarization states are physical, and the others are removed by gauge structure. That is a technical statement with a simple consequence. Light has transverse polarizations. This symmetry also helps explain why the photon is massless. A mass term would spoil the gauge structure, and the observed long-range force reflects that. If the photon had even a tiny mass, electromagnetic fields would decay over large distances, and the inverse square law would subtly fail. Experiments constrain any photon mass to be extraordinarily small, consistent with the symmetry-based expectation. The photon's masslessness connects back to Chapter 5. A massless excitation must move at c in vacuum, and it has no rest frame. That is not an extra rule added to photons, but a consequence of how energy and momentum relate for massless quanta. The geometry of space-time and the structure of the field agree on the same conclusion. So the modern definition begins to lock together. The photon is a massless spin 1 excitation of the electromagnetic field, shaped by gauge symmetry. It is also a quantum object whose state can be superposed, spread out, and interfered. The definition is compact, but it compresses a century of conceptual struggle. That sounds technical, but the payoff is practical. The same framework predicts the spectrum of hydrogen, the magnetic moment of the electron, and the behavior of light in matter. It explains why atoms are stable, why chemistry has patterns, and why materials have optical properties. It also predicts tiny deviations, small shifts and corrections, that become tests of the theory's depth. Now, the documentary must address a phrase that appears everywhere in popular explanations. Forces happen by exchanging photons, and the phrase is both useful and dangerous. Useful because it hints that interactions are quantized and mediated by fields. Dangerous because it can suggest little pellets flying back and forth like tennis balls. In QED, charged particles interact through the electromagnetic field. In calculations, that interaction is represented by photon exchange in Feynman diagrams. Those diagrams are not literal cartoons of events in time, but organized terms in a perturbation expansion. They help us compute probabilities, and they encode conservation laws at each interaction point. Some of those photons are real, some are virtual, and the difference matters if we want to stay honest. The distinction is not about existence versus non-existence in a casual sense. It is about whether the photon corresponds to a free propagating excitation that could be detected as an independent particle. A real photon is on shell. Its energy and momentum satisfy E equals pc, and it can propagate long distances and be detected as a separate particle. It can be prepared in a beam, reflected by a mirror, filtered by a lens, and counted by a sensor. In a vacuum, it travels along null paths, and its phase evolves predictably. A real photon can be counted by a detector. It can leave an atom, travel through space, and end as a click, as our opening hook described. Even if its quantum state is spread out, the detection event is localized. The click is where energy and momentum are deposited, and where the field and matter exchange a discrete unit. A virtual photon is not a tiny hidden particle flying through space in the same way. It is an internal line in a calculation, a way to organize amplitudes. It is part of the mathematical machinery that connects initial and final states. If you change the gauge or the computational method, the virtual photons in the middle can look different while predictions remain unchanged. Virtual photons can be off-shell. Their energy and momentum do not obey E equals pc, because they are not free detectable particles. They are constrained only by conservation at the interaction vertices and by the integrals that sum over possibilities. Off-shell does not mean breaking physics. It means the intermediate bookkeeping is not required to match the free particle relation. They exist inside the mathematics of an interaction. They are not directly observed, and treating them as literal objects can create false pictures. Still, the exchange language points to something real. The electromagnetic field couples charges, and that coupling produces measurable forces. Repulsion and attraction can be computed from QED. The results match the Coulomb law at ordinary scales, then add small quantum corrections. Those corrections include effects like vacuum polarization, where the vacuum behaves as if it slightly screens charge. At everyday distances, the corrections are tiny, but their existence is a reminder that empty space participates in the interaction. So when we say two electrons repel by exchanging photons, we mean their interaction amplitude is built from field couplings. We do not mean a stream of little bullets. The field is the mediator, and the diagrams are the accounting system. The language is a metaphor that points toward a calculation, not a hidden mechanical story. This matters for solidity. The feeling of a table resisting your hand comes from electromagnetic interactions and quantum statistics in matter, not from hard classical contact. Electron clouds in atoms repel when pushed together, and the Pauli exclusion principle prevents electrons from all collapsing into the same low-energy state. What feels like a solid barrier is a layered quantum effect. Fields, charges, and statistics acting together. Chemistry also lives here. Bonds, molecular shapes, and the stiffness of materials depend on electrons and the electromagnetic field obeying quantum rules. The sharing and exchange of electrons in orbitals are stabilized by quantized energy levels, and the forces between atoms are electromagnetic at their core. Even the colors of materials are shaped by which photon energies are absorbed or reflected. Yet we keep the promise modest. QED explains the interaction structure, but everyday objects are many body systems where approximations and emergent behavior dominate. A crystal lattice, a protein, or a living cell is not computed from first principles in any simple way. The fundamental laws set the stage. but collective behavior writes much of the script. Now we turn to the vacuum, because the word empty is one of the biggest lies in physics. In QFT, the vacuum is the lowest energy state of fields, not nothing. It is the state with no real particles present, but it is still a state of something. The fields remain, and their quantum nature forbids perfect stillness. Even in the vacuum state, fields have fluctuations. The field cannot be exactly zero everywhere, because quantum uncertainty forbids perfect stillness. The vacuum has a restless baseline, a minimum jitter that cannot be removed. You can cool a system, isolate it and shield it, but you cannot make the field's ground state behave like classical emptiness. These fluctuations are not always directly visible. They become visible through their effects on measurable quantities. Often the vacuum reveals itself indirectly, by shifting energies, modifying forces, or changing decay rates. The vacuum is like a background texture that only shows up when you place something against it. One famous example is the Casimir effect. Two uncharged conducting plates placed close together experience an attractive force. In a clean laboratory setup, the plates are aligned like parallel mirrors, and the gap between them is made extremely small. The force is weak, but it is measurable, and it grows as the plates approach. The force can be understood as a change in the allowed vacuum modes between the plates. The vacuum pressure outside differs from the vacuum pressure inside. Between the plates, only certain standing wave patterns fit, while outside there is a richer spectrum of modes. The imbalance produces a net push inward, as if the vacuum itself exerts pressure. This is not mystical energy pulled from nowhere. It is a difference in the field's zero-point structure caused by boundary conditions. The plates change what field configurations are allowed, and the vacuum responds. In plain terms, the emptiness is shaped by the presence of matter, and that shaping has a mechanical consequence. Another example is the Lamb shift. Hydrogen's energy levels are slightly shifted from the simple Dirac prediction. In the early days of quantum theory, the Dirac equation seemed to give a complete answer for hydrogen. Then precision spectroscopy revealed a tiny splitting that should not have been there. That discrepancy became a landmark because it demanded a deeper theory. That shift arises because the electron interacts with vacuum fluctuations of the electromagnetic field. The vacuum subtly dresses the electron's behavior. The electron is not a bare point with fixed properties, but a charged excitation coupled to a fluctuating field. The coupling modifies the effective potential the electron experiences, nudging energy levels by a small but measurable amount. Spontaneous emission is another vacuum story. An excited atom can emit a photon even in perfect darkness, without an external trigger. Classical intuition wants a cause, like a passing wave that shakes the atom loose. Quantum theory answers differently. The combined atom field system has an unstable excited state. The vacuum provides available modes for the photon, and the probability leaks into them. In QFT, the vacuum contains modes the atom can couple to. The emission is stimulated by the field's ground state fluctuations, not by a classical wave. The rate of emission depends on the density of available modes, which is why cavities can suppress or enhance emission. By changing the electromagnetic environment, you can change how quickly excited atoms decay. This reframes the idea of emptiness. Even when no real photons are present, the electromagnetic field is still there, and it still has structure. The vacuum is not a blank stage, but a particular configuration of the fields. It is the baseline from which excitations are defined, and it can be reshaped by boundaries, materials, and geometry. The vacuum is also not a universal constant in every context. What counts as vacuum depends on the observer and the background, especially in curved spacetime. In accelerated frames or expanding universes, the division between vacuum and particles can shift. The field remains, but the bookkeeping of excitations can become observer-dependent. This is where quantum theory and cosmology begin to touch. If spacetime expands or accelerates, the notion of particle content can change. A state that looks empty to one observer can look populated to another, because their definitions of positive frequency differ. The idea is subtle, yet it is one of the places where photons become a probe of deep structure. Now we return to photons as creators and destroyers of matter. The photon is pure field excitation, yet at high energies it can become mass. This is not alchemy, but conservation laws applied to quantum fields. Energy and momentum can be rearranged into different excitations when interactions allow it. Near a nucleus, a high-energy photon can produce an electron and a positron. The nucleus is needed to take up momentum and satisfy conservation laws. Without a nearby heavy object, a single photon cannot turn into a pair in empty space, because momentum would not balance. The nucleus provides a recoil partner, letting the process proceed. This is pair production. Energy becomes matter, and the electromagnetic field's quantum turns into two excitations of the electron field. The threshold is set by twice the electron's rest energy, plus whatever kinetic energy the pair carries. In detectors, this can appear as a gamma ray vanishing and two charged tracks spiraling away in a magnetic field. The reverse also happens. An electron and positron can annihilate into two photons, typically gamma rays. The two-photon outcome protects momentum conservation, and it reminds us that the photon carries momentum even with zero rest mass. In the center of mass frame, the photons fly back to back, equal in energy, like a perfectly balanced recoil. These processes are not rare curiosities. They occur in particle detectors, in astrophysical jets, and in the high-energy universe. They occur near neutron stars, around black holes, and in the aftermath of violent cosmic events. They also occur in medical imaging, where positron emission tomography relies on annihilation photons detected in coincidence. They also underline a central theme. Particles are not permanent little objects. They are excitations that can transform when fields interact. The identities we assign, photon, electron, positron, are stable patterns in the field dynamics, not indestructible marbles. Under the right conditions, the patterns convert and the bookkeeping changes accordingly. Now we widen the stage to the early universe, where fields dominate the story. In the hot beginning, particles and photons were in constant creation and destruction. The universe was dense, opaque, and filled with a plasma of charged particles and radiation. Photons scattered so frequently that light could not travel far, and the concept of a free long-range photon was temporarily muted. At high temperatures, the vacuum we talk about today was not the relevant state. The field configuration and its energy landscape could be different. In many theories, symmetries that are broken today may have been restored at high energies, changing particle properties and interaction strengths. The ground state of the fields can shift as the universe cools, like a material changing phase. Cosmology uses quantum fields to describe primordial fluctuations. Tiny quantum variations can be stretched by expansion into large-scale density patterns. The remarkable claim is not that the universe is quantum, which is expected, but that quantum noise can become the blueprint for galaxies. The smallest jitter becomes the largest architecture. Inflation is one proposed mechanism. A rapid early expansion could amplify quantum fluctuations, leaving seeds for galaxies and the CMB anisotropies. In visual terms, imagine a microscopic ripple on a field being pulled outward until it spans astronomical distances. The ripple's origin is quantum uncertainty, yet its imprint becomes a temperature variation across the sky. We keep the claim careful. Inflation is strongly supported by some observations, but the detailed model and the underlying field remain uncertain. Different inflationary potentials can produce similar broad predictions, and the microphysics is still debated. What matters here is the conceptual bridge. QFT provides the language for fluctuations, and cosmology provides the canvas. Still, the conceptual link is profound. The same quantum vacuum that shifts hydrogen levels may have helped sculpt the universe's larger structures. It is a single idea expressed across scales, from the atom to the cosmic web. That scale bridging is one reason photons remain so central to the story. They connect the microscopic rules to macroscopic evidence. Vacuum energy enters here as a tension point. Quantum fields predict a vacuum energy density, yet the observed cosmic acceleration is far smaller than naive estimates. If you sum zero-point energies up to very high frequencies, the result is catastrophically large. Yet the universe expands as if the vacuum energy is small, not enormous. This mismatch is the cosmological constant problem. It is one of the sharpest signs that our understanding of vacuum and gravity is incomplete. The problem is not merely a numerical annoyance, but a conceptual collision between two successful frameworks. QFT handles the quantum vacuum, and general relativity handles spacetime curvature, yet their combination resists a clean reconciliation. So the vacuum is not just a laboratory curiosity. It may be tied to why the universe expands the way it does, and we do not yet have the final answer. The emptiness between galaxies is not inert, and the baseline state of fields may influence cosmic fate. The photon, as an excitation of those fields, becomes a messenger not only of distant objects, but of the vacuum itself. Now we return from the cosmic scale to the practical act of counting photons. Our modern definition must still connect to the click we can record. The theory earns its keep when it predicts what instruments will do. It must explain why a detector registers discrete events, and why those events follow statistical patterns. A CCD detects photons by converting them into electron hole pairs in silicon. The charge is stored and read out as a pixel value. Each pixel is like a tiny bucket, collecting charge during an exposure, then handing it off during readout. The number of collected electrons is proportional to the number of absorbed photons, within the limits set by noise and quantum efficiency. A photomultiplier tube detects photons by ejecting an electron from a photocathode. That electron triggers a cascade, producing a measurable pulse. The cascade is a chain reaction across dinodes, each step multiplying electrons by secondary emission. The final pulse is large enough to be counted with classical electronics, even when the initial event was a single quantum. Avalanche photodiodes do something similar in a solid-state form. One absorbed photon initiates a controlled breakdown that amplifies the signal. The device is biased near a threshold, so a single carrier can trigger a rapid multiplication. In single photon mode, the output is a standardized pulse, which is why these detectors are used in quantum communication and LiDAR. Superconducting detectors go further. Transition edge sensors and nanowire detectors can register single photons with high efficiency and timing precision. A nanowire can be cooled until it sits on the edge of superconductivity, and one photon can push a tiny region normal, producing a voltage pulse. The timing can be measured in tens of picoseconds, turning a quantum absorption into a precise timestamp. These devices do not see a wave directly. They register discrete absorption events, then amplify them into classical records. Even when light behaves like a wave in propagation, detection is granular because matter's energy levels are granular. The detector's microscopic structure forces the exchange to come in quanta, and the readout makes the result irreversible. This is how we detect photons from distant galaxies. A single quantum can travel for billions of years, then end as one count in a sensor. Along the way, it may be redshifted by cosmic expansion, its wavelength stretched as space itself changes. Yet its identity as a photon, an excitation of the electromagnetic field, remains intact across that journey. The count is small, but the inference is large. By collecting many photons, we reconstruct spectra, distances, motions, and the history of cosmic expansion. We measure Doppler shifts to infer velocities, and we measure absorption lines to infer chemical composition. We even use photon arrival times to study transient events, where the universe changes in seconds. Even the CMB is a photon census. Instruments measure tiny differences in photon energy across the sky, mapping early universe fluctuations. The anisotropies are subtle, at the level of parts in 100,000, yet they encode the seeds of structure. The CMB photons are ancient, and their distribution is a fossil record written in radiation. So the photon remains the universe's messenger, but the messenger is now defined by fields and symmetries. The click is an interaction between quantized fields. What arrives is not a classical wave crest and not a tiny pellet, but a quantum state that can deposit energy in one localized event. The theory that predicts the click is a theory of fields, and the photon is one of its simplest excitations. Now, we gather the chapter's threads into one modern statement. A photon is a quantized excitation of the electromagnetic field, constrained by gauge symmetry. It is identical to every other photon with the same quantum numbers. It can be real and detectable, or virtual as an internal part of an interaction amplitude. The vacuum it moves through is not empty. It is the ground state of fields, with fluctuations that leave measurable fingerprints. Those fingerprints show up as forces between plates, as shifts in atomic lines, and as the very possibility of spontaneous emission. The vacuum is quiet only in the classical sense, not in the quantum one. This modern picture resolves some older tensions and deepens others. It explains why light is both wave-like in propagation and particle-like in exchange. It also explains why photons have no individuality, and why that sameness is essential for interference and coherence. Yet the explanation comes with a price. The world is not made of objects first, but of fields whose excitations masquerade as objects. Yet it also sharpens the mystery behind our hook. a field excitation can cross the observable universe and still arrive as one discrete local event. The propagation is spread out, the detection is pinpoint, and the bridge between them is probability. We can predict the statistics with exquisite accuracy, but the single click still feels like a revelation, and it forces a final, quiet discomfort. If the vacuum has structure, and if fields are fundamental, then what we call nothing is already something. The emptiness between stars is a state of fields, and the ground state carries fluctuations that can be measured. The photon, born from that structure, becomes a guide to what existence means in modern physics. Transition to the last chapter. With the modern definition in hand, we return to the biggest scale question about light and what remains unresolved. We ask what photons ultimately reveal about reality's stitching. We ask where QFT and gravity still fail to agree, and why light sits at the fault line. Cosmology is mostly photon work, from optical and infrared to X-ray and gamma skies, and each band reveals different physical engines. In visible light, we trace starlight and galaxies, while infrared slips through dust to show cooler clouds and newborn stars. X-rays and gamma rays, by contrast, spotlight shocks, jets, and accretion, places where gravity and magnetism push matter into extremes. Spectral lines are atomic fingerprints, set by quantized energy levels, and their precise wavelengths let us read the chemistry of distant gas. Line widths and ratios reveal temperature and density, while Doppler shifts map rotation and outflows across galaxies. In strong fields, Zeeman splitting and synchrotron emission hint at magnetic geometry, turning faint polarization into a kind of compass. Redshift turns photons into rulers, linking distance to expansion through the Hubble-Lemaitre law, a relationship first debated when galaxies were still nebulae. As space stretches, wavelengths stretch too, and that slow reddening becomes a time machine, each spectrum arriving as a dated postcard from earlier cosmic eras. Now we widen the stage to the CMB, a near-perfect black body with anisotropies around 10 to a 5. On screen it looks like mottled static, yet it is the afterglow of a hot plasma cooling into transparency. Its acoustic peaks encode early sound waves, frozen when recombination let photons stream freely, and their spacing pins down cosmic geometry and matter content. Polarization separates E modes from the hunted primordial B modes, a subtle swirl pattern that could betray inflation's gravitational ripples. Yet photons hit limits, since the early universe was opaque before recombination, and scattering erased any earlier images. We need neutrinos and gravitational waves to see earlier chapters of cosmic history, because they slip through matter almost untouched. At this point, we return to the click and the measurement problem. Copenhagen, many worlds, and objective collapse disagree, and photons sit at the center of what counts as an outcome in detectors and in our theories. A single absorbed photon can trigger an avalanche of electrons, turning a probability amplitude into a macroscopic record. Yet why that record is definite remains unsettled. Near black holes, photons brush quantum gravity, from Hawking radiation to transplanckian puzzles and information loss, where horizons behave like thermodynamic surfaces. Revisit the opening journey, long in our clocks but null in proper time, with no photon rest frame and no valid view from light itself. A photon is a quantized electromagnetic field excitation, carrying energy and momentum, moving at c in vacuum, interfering via amplitudes, and telling the universe's story. Photon explained, and what is a photon meet quantum physics, wave-particle duality, quantum mechanics explained. Photon, quantum physics, what is light? Science, explained. Physics, quantum mechanics. Tonight we followed light from a familiar glow into unfamiliar rules, watching it act like a wave in space, yet arrive as counted indivisible clicks. We traced the long argument from rays and ether, through Maxwell's fields to Planck and Einstein, where energy came in quanta and the photon stopped being optional. Then the story widened because single photons still interfere, momentum rides on frequency, and relativity turns their paths into null lines through spacetime. While quantum field theory says the thing travelling is an excitation of a field that already fills the vacuum. Along the way, the three headline strangenesses began to rhyme rather than compete, because they are different shadows of one framework seen from different angles. Wave, particle duality becomes a rule about information, because interference survives only when alternatives remain indistinguishable, and it fades when which-path knowledge leaks into the world. Massless momentum becomes a rule about symmetry, because a photon cannot rest, and so its energy and frequency are welded together as two names for the same invariant bookkeeping. And no aging becomes a rule about geometry, because light does not carry a clock along its route. It simply connects events on the boundary of what can influence what. Yet the most stubborn thread remained in our hands, because the photon's smooth amplitude can spread across slits, lenses, galaxies, and expanding space, while the detector insists on a single, irreversible outcome. Quantum theory predicts the pattern with exquisite accuracy, and quantum field theory tells us what is being excited, but the bridge from possibilities to one fact still feels like the universe withholding a final sentence. Even our vacuum, the stage we thought was empty, turns restless and observer-dependent, hinting that a photon is not just a particle, but a relationship between fields, observers, and space-time itself. And when we use photons to read the cosmos, spectral barcodes, gravitational lensing, the CMB's faint ripples, and the redshifted stretching of wavelengths, we learn that light is not merely illumination, it is how the universe keeps records. All of that leaves us with a picture that is strangely coherent, even when it refuses to be simple. A photon is not a tiny billiard ball, and it is not a classical wave sloshing with continuous energy, but a quantized excitation of the electromagnetic field whose evolution is wave-like, and whose exchanges with matter are discrete. Between emission and detection, the most honest description is not a hidden trajectory, but a structured spread of amplitudes constrained by symmetry, by causality, and by the geometry of space-time. The click is not where the photon was all along, it is where the world finally demanded an answer, and recorded it. And still, the open doors matter, because our best theories do not yet agree on the vacuum's weight, on gravity's quantum language, or on why one outcome is chosen at all. The hunted B modes may or may not appear, neutrinos and gravitational waves may eventually show us behind the photon curtain, and some deeper framework may reframe the measurement problem as a limit of our current questions. Until then, the photon remains a meeting point, where quantum probability, field excitations, and space-time geometry intersect. Quietly, precisely, and with just enough mystery to keep the universe from feeling finished. So what is light, really? An object, a wave, or something that slips through the cracks of time itself? It is all three in a careful sense, because a photon is a field excitation that spreads as amplitude, transfers energy and quanta, and travels on null space-time paths where proper time does not accumulate. The opening riddle was never asking for a single label. It was asking what kind of world could make such behavior inevitable. When we chase the photon across the observable universe, we are really chasing the rules that stitch reality together, and discovering that what it is depends on how and where it must be known. Perhaps the strangest part is not that a photon takes no time, or that it interferes with itself, but that it can be both everywhere it could be and only one place it finally is. Light feels like the simplest thing we have, yet every photon carries a reminder that the universe is not made of objects alone, but of relationships between fields, measurements, and the shape of space-time. If you want to keep listening past the last scattering surface, follow the next clues, polarization maps, neutrino backgrounds, gravitational waves, and let the question stay open a little longer.